Good afternoon, everybody. This is Parisa Jurabchi from Aris Environmental. I can't get any feedback to know if the session has started or if there is the technician online at the moment. So if there are any other co-organizers or if any of the organizers are online and they could give me some feedback, I would appreciate that. And so I'm very pleased to let you know that we have a fantastic array of presenters this afternoon. And I would like to view the session and all the presenters. One logistical note is that our presentation will start at 2:30 p.m. Mountain Time, and this is a minor typo in the program. There will be 5 minutes of time at the end of every presentation for questions. So if there's not enough across a variety of site types and contaminants, ranging from in situ biological, chemical, and physical treatments to reactive transport models and data digitization. We are very thankful for SNC-Lavalin for sponsoring this session and have the following video from them. So if you could please roll the video from the sponsor, please. Thank you.
SNC-Lavalin was founded in 1911. We are a leading engineering and professional services group with over 40,000 people around the world. Our Environment and Geoscience group has one of the most comprehensive environmental consulting teams in Canada. Our experience includes conducting thousands of projects across multiple industries, including retail and manufacturing, oil and gas, utilities, mining, transportation, chemical and metal processing, and land development. From concept to closure, we have experience spanning the entire project lifecycle and decades of experience with the environmental regulatory system. Our teams seek innovative solutions to quantify, reduce, or remove environmental risks and liabilities. We help clients with environmental site assessments, risk assessments, remedial options analysis and action plans, remediation and reclamation, risk management plans, hydrogeology, groundwater modeling, as well as expert review and litigation support. As an organization, we are committed to being a corporate citizen and active in the communities in which we operate. Talk to one of our consultants to learn more about our unique environmental solutions.
I'm sure everyone was able to see the video. We had some technical difficulties, but I think in the interest of time, we can go ahead with the presentations. And so I'm going to switch over to Jean Perret, who is going to be talking about in situ remediation. Jean Perret is with Chemco with nearly 2 experience and in situ methods of remediation. And I see that
Hello, Parisa, do you hear me?
Yes, John, it's working well. Thank you.
Good. Let me just check here on my audio. Must be better. Does it sound okay with you, Parisa?
Yes, sounds good.
I don't seem to hear. Beautiful. So if I'm sharing
Yes,
my screen now, people would see a lot
you
of
can
things.
switch.
Now, is the presentation up?
Yeah,
Good.
it is. Yes, thank you.
Yeah, you're welcome. And then, there we go. So hello everybody. Thanks for attending this kind of unique RemTech. I've been part of that event since 2007, so it's been 13 years in the making, and I'm sitting comfortably in Quebec right now rather than in the Fairmont, so it's kind of different. Now, as of today, we'll be talking about update on the activated carbon that are used for contaminant control and site remediation. This is a bit of a lesson learned, state of practice. I did a lot of research and trying to find not just vendor data, but also data that originating from the academic industries and also from different governmental agencies to try to grasp where we are at with the use of activated carbon for contaminant remediation. So my next, just a second. Yeah, there we go. So presentation summary, I'll talk about the capture, the treatment mechanism. We'll talk about back diffusion, how it might affect your site and your meeting of your remedial objective. We'll talk about activated treatment capabilities and obviously a few case studies at the end. Now, when you're looking at sites, there's an array of technology that could be applied. We're talking dig and haul, getting material to landfill. There was some great speed this morning about excess soil regulation being enforced in Quebec, in Ontario, and BC. So, you got to navigate within the legal, but also looking at your customer objective. I always say, when we do assessment from site all across Canada, that we look into time and money. So we got to look at what's feasible, what's doable, what's the most cost effective. So today, obviously, we're focusing on activated carbon sorption and treatment technologies. The literature that I've used is fairly recent. I'm talking about the US EPA document that was issued back in 2018, the NAVFAC report that was issued on September 2019, so about a year ago, and then some other university papers and so on. So they'll be recognized at the end, through the acknowledgement slide. The first thing I'd like to talk is when we're trying to remediate site, and especially in an in situ matter. Obviously, if you're digging and hauling, there's not really a big issue in the sense that you're going to clean walls at the bottom on the site excavation. Guess what? Hopefully, it's done. When you're dealing with the technology or contaminant that is located in situ, well, guess what? There's a lot of contamination that would be, sorbed into these very fine clay layers or finer grain geologies that would typically liberate, contamination as the groundwater flows against these. So even if you remediate quickly, the contaminant of concern in the sand seam, and that's a good example here that I'm giving you as far as visualization of that by diffusion, is you have these clay layers that might have sorbed contamination in, and that would trickle out like for a very long time. So that video that I'm going to show you here, is typically they're flowing a tracer, a fluorescent dye, through a lens of a 2D like sand and clay, and as the water that's simulating groundwater flow crosses, you could see it's flushing out all of the tracer, but you could see like these fine plume that are keep desorbing, and that's what's usually a big concern in trying to get site closure over time, because if you're working, and I'll give an example, through chemical oxidation processes, like peroxide would last, 3 to about 20 days to the max. Persulfate about, on the sodium side, about 3 months. So you got to be able to cope with these very slow diffusion rate where the contaminant will make itself available, and at one point in time, you got to be able to treat it and capture it. So that's how the use of activated carbon, and everybody kind of know activated carbon to be used in pump and treat system or into potable water treatment system. If you have a Brita filter at home, guess what? It's activated carbon in there. So it's a very porous structure, and you could see like the very shape and how hollow these things are. So very high surface area, but also a lot of pore, like a sponge. Now, if we're like focusing down on these pores, and it's going to be very interesting, I'll direct your attention first to the right hand side of the slide, and looking at, there's 3 different pores there. So the macro pores are the very big opening where the contaminant that is in the groundwater would essentially sorbed in, and it would get into a mesopore. And then you got the micropore. And it's very important to distinguish, what is a macro versus a meso versus a micropore, because we're talking about diameters here. So typically, the micropore are about 50 nanometer in dimension, and there's some places where treatment might not be able to occur. So understanding that we use activated carbon in the subsurface, so it's injected, put into the aquifer, mixed with the soil, the water will come in contact with that, and there'll be a different mechanism of absorption that'll happen. What I've highlighted on the left-hand side was that macro and mesopore are kind of the highway. So that's typically where the water circulates and moves, and that's typically where the treatment will occur if you have a treatment pathway. But in the micropore, it's way too small. There's no biological activity that goes in there, so it's very important. Now, again, focusing on the left-hand side of the slide, just looking at the difference in size, like we're talking 177 micron for the opening, or the particle size for the granular activated carbon. But you're moving to a powder less than 40 micron, and the other technology out there, like the colloidal, is 1 to 2 micron. But again, I'll point out your attention to the size of a bacteria. So if you're trying to achieve other mechanism than absorption with your contaminant, because once it's in the carbon matrix, you're looking at getting it treated. So what we can see is that the bacteria will not be able to enter within the micropore matrix. So, and that's going to be an interesting mechanism that we'll discuss in the future slides. So just keep that in mind, that treatment, if on activated carbon, mostly, especially if you're talking about biological treatment, happen at the surface. And this is typically a shot of a biofilm that's forming on top of a granule of activated carbon, where you could see the bacteria. But again, remember, because of the size of the micropores that is smaller than bacteria, they don't go in there. So there's no treatment. The contaminant will get there, but not the treatment or the biological activity. So one way to counter that is not to use biological pathways of degradation, but use more so electron transfer, which are typically chemical reactions. So obviously electrons are much smaller than this. So that's giving you an example here of a product. It's called EHC+, where we're combining a few components to go at chlorinated solvents. First, the little blobs of 3 greens and gray that are moving on your screen right now are TCE, so trichloroethylene, and they would get typically reduced from direct contact with the zero valent iron, which is a normal abiotic pathway of treatment. Now, once it gets sorted into the carbon matrix, you can still do that electron transfer exchange, and that comes with very low ORP mechanism. So that's typically what's happening there, and you could see the treatment being still achieved within the pore matrix. Now, the other pathways that are occurring at the same time for the degradation of the contaminant is you ferment a fermentable organic carbon substrate, the FOC, and that's creating volatile fatty acid, and that typically again releases gases, hydrogen here, that would come and react. It will also help with regenerating the iron to get it more reactive, and then at the end you'll have the bacteria themselves that will come and populate and help out. So as you could see here, like when you're trying to treat out contamination that is sorbed within the matrix of carbon, it's good to focus on different pathways. The other thing that you got to think, and I'll mention it again later, is that once you've sorbed into that micropore, you know, it might take a very long time for the contaminant to come out of there and come to be available for destruction through electron transfer or through direct contact at surface with biological pathways. So it's important to remember that if you're putting an amendment down there to help with the sorption of the contamination in the carbon matrix, it is a long-lasting amendment. So the good thing about carbon is quickness. So that's an example here where we could see that, I'll again direct your attention to the timeline at the bottom. So you could see that within 3 months, typically, we went down from 600 micrograms per liter to lesser than close to none detect. So it's quick, it's appealing, but you got to remember that what's sorbed in there, you know, could eventually come out, and that's why you need that treatment mechanism to be combined with it. So in the general understanding of findings and explaining how the carbon matrix working, you could see here first the activated carbon. Sorry about that. So the activated carbon are applied in an in situ basis to deal with a wide range of organic contaminants that are mostly in the groundwater. Physical absorption, as we've seen through the different type into the different type of pores, the dominant removal mechanism, and it would get you a quick decrease of groundwater mass. Now, you can have various degradation mechanisms that are used to treat. So whether you're using bioremediation, what are aerobic chemical reduction, and I'm missing one in there, which is abiotic pathways. So which would be chemical reducting processes. So that's all these type of pathways that we want to couple with the contaminant of concern to get it to get. Now, contaminant is sorbed into the micropores, but it won't degrade directly. So it has to have time to diffuse, and you have to have amendments there. So again, long-term amendments, as I've mentioned it, you need to be careful with a few type of compound, like especially like benzene and vinyl chloride. And it's very simple, as these molecule has a very good partitioning into the water phase. So if there's something that has more affinity with the carbon matrix than benzene or vinyl chloride in your contaminant mix, it will essentially get bumped out. So you got to be careful about these contaminants where, you know, they'll be sorbed, but you know, they might essentially be displaced very easily by other compounds that have more affinity with the carbon. And again, we're talking about groundwater contamination here. So if you have NAPL on your site, it's usually not the best way to do it. You got to try to remove some of the contamination first, and then, you know, act and try to move in with another. But it's usually not applicable to very high concentration in the groundwater. Same thing is true with soil. If you have some residual ganglion NAPL that is slowly dissolving, yes, possibly. But if you have like in the 10,000 to 20,000 milligram per kilogram in soil, then guess what? Might not be your best technology pick, you know, for yourself. today we'll be focusing mostly on chlorinated solvent and petroleum hydrocarbon for this technology, but there's other type of compound like chlorobenzene and others that can be dealt with that. So we got to be, obviously not all compounds here listed here are available or can be dealt with activated carbon, but again, reviewing what's out there, and that's the most exhausted list I could find, that we've seen in the marketplace. And so you got different products which are either in granular, powder, or colloidal form. Some are already pre-mixed or impregnated with treatment or amendments. So you're emplacing the technology and it will start reacting directly. Some other would need to combine it with something else. So, just to mention like the plume stop or the Petroflex, where it's only activated carbon, which is colloidal form is suspended in solution, but you got to add up some nutrients. You got to add up some other stuff with it to make sure that you have a treatment pathway that is viable. And so most of them have been used in sites now all across the US or Canada or internationally. So there's a lot of the documentation that's available from the different vendors of these. I'm not going to put any judgment today about which is which, because which would be the best or not, in the sense that, with any technology, and Chemco is a technology company, there's always something that fits a site properly. So there's some niche design that might favor one technology over another. And again, that's the most exhausting list I could find of different amendments that are out there. The way these things are applied is fairly simple. Most of the time, we're trying to control a plume. So we're talking about groundwater migration. It's either to protect a sister property or prevent entering of contamination within an existing property. So a PRB, that's a plume control. Now we could do hotspot, as I've said, like if you got these very tight geologies where the contamination is sorbed and you're trying to prevent or control back diffusion issue, as we've established early on in the presentation, then guess what? That's a good way of dealing with it. And obviously, if you just have a plume or trickling plume, and you've cut down the dragon's head, but you're just chasing the tail now, guess what? It's a good way of a cost-effective way to control it. Now, how it's in place within the soil itself? Well, obviously injection. So, as activated carbon is non-soluble, we're talking about injecting a slurry to direct push. There's some hydraulic or pneumatic fracturing that could be done also to exactly place, the contamination into, not the contamination, but the amendment directly, let's say in a bedrock or in a fine-grained geology where, direct push would not be able to do. And obviously you could do direct placement. So if you do have an open face, like you dig out all the soil, there'll be some contaminated groundwater coming back into the excavation and you want to deal with it. Well, guess what? That's a good way of doing it. So direct placement into excavation and soil mixing. The other thing that's very important to understand when you're dealing with carbon as a potential treatment mechanism for your contaminant of concern is the assessment of the remedial performance afterwards. So there's a lot of cases where I've seen where you inject through direct push and you might get into the because of pressure that's applied into the packing of your well. Well, guess what? Your monitoring well is now typically going to be showing very good results and removal for a very long time. So it's normally recommended that when you do a carbon emplacement injection and you're working very close or within the radius of influence of your existing well, that you position some new monitoring well after the fact. Because as soon as you get some minimal quantities of carbon in there, and that's a presentation, some of the slide that I've taken from the MAXAM, or which is now Bureau Veritas presentation back from 2017, where they've looked at how much carbon would impact the typically create an interference with the contaminant concentration. And we're talking about 100 milligrams per liter. that they find. So if you're sampling from a site that was injected with activated carbon, well, guess what? It is important that the vial will settle so that they can get, but you could see here the different concentration of carbon, and it will impact, in the analytical, so they need to be aware of that.
Sorry, Jean-Pierre.
Yeah, go ahead.
Interject. Just one moment. I realized we started a few minutes late, so we're just past 1 o'clock. So if I could just ask you to take maybe another 3 minutes to wrap up, that'd be good.
Yeah, well, guess what? We'll manage.
Okay, great.
So,
thank you.
Hey, no worries. So, I got 2 case studies. One is on petroleum hydrocarbon contamination, and the second one would be on a chlorinated solvent. So, I'm going to flip quickly to these in the sense that, they'll be available for you to see afterward. So, this site, was they typically had a diesel fuel UST that was there, and they needed to have, like, you got to focus again on the remedial objective for the customer. So they need 4 quarters of clean water before they could do the transaction. So in that regard, that's typically the overview of the site. You could see here that in the groundwater here, we're in the clay matrix. So we're talking about rebound. And so even if you inject persulfate or chemical oxidant, you might get at what the contamination that is not sorbed very deeply, but you might have a long back diffusion process, and that's obviously an issue to get to the remedial objective that you're seeking. You can see here the contamination level for the F2s and the F1. So we're talking like quite a significant amount in different monitoring wells. And so I'll direct you also, and that's typically the groundwater. So the F2s were, and some BTECs were mostly present in the contamination. Now, I'm going to pass on how this thing was typically done, but they went and injected some BUS 200 within the zone of concern in the impacted area. So what you could see here, now I'll put my attention to the results. So we're talking about 4 rounds of injection. So there was typically 4 quarters. You could see here the dates ranging from May to February 2018. And you could see the results, like, stunning. It's great removal. There were a blimp there on the benzene, but realistically, none detect all across the border. So we know the absorption process work. Now, it would be interesting to see further down in time, if, and that's typically like a graph showing the same thing. We were quite below the standard for all the contaminant of concern, especially F2s, over the course of that study. So, so they wanted some certainty. It's going to be very long for treatment, so that's good. And they got the objective. The second case, it's a EHC plus case, and I'll flip right through that in the sense that I don't have a lot of time left, that we started late. But you could see here the plume, which is in pink, and then the 2 reactive wall that were put in. And over the course of time here, and it's after 1 year, you could see the previous and after, we were able to get the contaminant level to whatever the criteria was for that particular site, which was in the US. And I'm going fast over these 2 things, but you could see typically the plume contour, between the 2 after a year of injection of the HC+. The slide will be made available to you guys. So before they cut me off, I just want to make sure that I cover the conclusion and lesson learned. So, oops, sorry about that. So first, in situ technologies. Important to perform bench scale before getting to the field, making sure we select the right amendments, the right form of carbon, and the right treatment substrate. If you have residual NAPL, it's fine to use. If you have a lot of NAPL, please try to remove it before using these type of technologies. The competitive absorption we've talked about it. It will affect the long-term effectiveness. So some compound like benzene, vinyl chloride might not absorb very good with the carbon. So you got to be able to cope with that, and also select an amendment that will last for a very long time. Post-injection monitoring will be performed in the long term. And think when you're putting carbon down there, it could, depending on the mass flux of contaminant, it could last decades. So you got to be able to come back there and validate performance, and if there's any kind of desorption processes that are happening from the micropores. If you have a fast flowing aquifer, well, guess what? If you have a, let's say the colloidal carbon, for example, it might get displaced before it settles. So it might not be stuck in the area where you want it to be. So you got to take that into consideration when you pick up your amendments. Obviously, additional research is needed to better understand these. But at this time, over the course of the last, I'd say, 5 to 8 years, AC-based amendments have shown that it's working, and they're providing very long-term and extended release treatment, targeting in years, to get your contaminant. And I'll skip through the last few slides that talks about Shemco, and I'm sure you've seen me a few times before if you've been around RemTech, just to say that we assess about 400 to 500 sites a year across Canada, providing niche design on these technology. And I'd like to thank the different partners that have contributed to the content of this presentation to launch the first technical session of the 2020 RemTech. Thank you again, and thank you, Parisa, for letting me finish, despite starting late.
Yes, thank you very much, John, and thank you for everyone for your patience as we had some technical difficulties. I received some notes indicating that the video didn't show earlier, but maybe we can, I wasn't sure if that was just on my end, but it seems like there were others who were having difficulty, so that may have a chance to broadcast that later, but in the interest of time, we will go. Next, we have Elizabeth Murray, who is a senior scientist with Earthmaster Environmental Strategies, and she will present experimental results on phytotechnologies.
Hello, everybody. I'm just going to swap this out here. All right, so I'm a senior scientist with Earthmaster Environmental, and we are environmental technology company based in Calgary, Alberta. So we specialize in all sorts of environmental services, but we also have a phytoremediation technology program that we do a lot of research and development on in the lab. So I'm just going to talk a bit today about some of that R&D work that we've been doing. So phytotechnologies, or the use of plants to address a scientific problem, it's quite amazing what plants can do. So we exploit their phytoextraction and phytostimulation abilities. So we use them to extract salt from contaminated soil, and we use the bacteria that colonize the roots to break down hydrocarbons. So that's the advantages that we take, that we make use of when we're using plants for remediation. The challenge, of course, is when you're working with contaminated soil, how do you get the plants to grow? We developed a technology along with the University of Waterloo called PEP systems, or plant growth promoting rhizobacteria enhanced phytoremediation systems. And that technology utilizes seed that we coat with bacteria. And once the seeds start to germinate, the bacteria will colonize the roots. And the bacteria actually provide plant growth promoting activities. They provide hormones that stimulate plant growth, and they also provide an enzyme that breaks down the precursor to stress ethylene. So you're able to short circuit the ethylene process when plants are grown in stressful conditions. So I'm going to talk a bit about the development work that was done with elevated salinity in soil. So this is some of the initial work that was done by the University of Waterloo, and they were looking at two different kinds of soil here. So they've got a medium salinity soil and a high salinity soil. And what they found is that when they grew plants on this soil, it made no difference if you had PGPR on that seed and co-localized PGPR with the plant root system as to how much salt that the plants could take up. So they knew from those experiments that the plants are limited on their capacity to take up sodium and chloride, and that the addition of plant growth bacteria had no effect on the ability of plants to take up the salt-related compounds. However, what they did find is that the presence of PGPR increased the biomass of the plant. So if you look at the bottom chart there, you'll see that when you compare the untreated or dark colored bars to the treated or light colored bars, you can see that the addition of plant growth promoting bacteria increases the biomass production by the plant. If you increase the biomass on a per meter squared area, you're going to increase the amount of salt you can take up in that plant from that particular area. So what they found from doing that initial work is that grasses, the plant of choice for the PEP systems technology, are able to remove approximately 65 grams of sodium chloride per kilogram of dried plant material. So we wanted to do a bit more development work on this technology and look at different ways to increase plant biomass when grown in salt conditions. So this initial set of studies was done looking at seed germination in the presence of produced water. And we worked with 2 different produced waters there, and you can see the contaminant profile listed below. So it's got quite a bit of chloride, a lot of sodium, as you would expect with produced water. And what we did was we set up germination plates, and we worked with 4 individual species, so annual ryegrass, perennial ryegrass, tall fescue, and tall wheatgrass. And they were plated individually, and we compared those seeds that were untreated to those that were treated with PGPR. We also added other additives onto the seed to look at whether we could also increase germination and hence eventual plant growth when we're growing in contaminated soils. The growing surface we used was a Walton filter paper. It was saturated with a produced water solution, and that solution ranged from 0 to 100%. And then we grew these plates in incubators for 25 degrees for 14 days. And these are some of the examples of results that you can get with this kind of information. So you can see the 4 different seed types here. The numbers across the top here represent the amount of produced water in that particular group of seeds. And then we plotted on a growth curve versus number of days. And you can see with these growth curves that you can get germination over the days, and as you increase the amount of produced water in there, the amount of seeds that germinate really level off. And that allows us to look at lethal concentration, or the concentration of produced water or the components in the produced water that are capable of killing or preventing germination of 50% of the population. And LC50s are a common number that we look at. Mean germination time is also one of the factors that we looked at, as well as percent germination. How many out of the 20 seeds did we put on the plate actually germinate? So if you look at just a subpopulation of a couple of these treatments, both of these seeds are untreated, perennial ryegrass on the left and tall fescue on the right. And you can see with increasing concentration of produced water, which I've translated into a milligram per liter concentration of chloride, you can see that you get reduced germination, or germination will happen, but it takes longer. And what that allows us to do is compare the different seeds' tolerance to produced water, as well as calculate the numbers that we can use to evaluate how PGPR is going to affect a seed's ability to germinate under these conditions. So what happens when we add in PGPR? And I've just taken the produced water and switched it over to milligrams per liter of chloride. So as we add PGPR to the seed and you compare the solid lines to the dotted lines, you can see for a particular color that as you put PGPR on the seed and these seeds start to germinate, the PGPR provide a tolerance or protective effect, so that more seeds are capable of germinating when they're treated with PGPR, and they're able to germinate at a much quicker pace. So with that kind of information, we can actually compare LC50 values. And this is an example of that. So when you look at the LC value in the various produced waters, and I've separated them out here, you want to compare the hatched box, which is the untreated control, to the solid one in the presence of our PGPR, which we call CMH3. So we can see for annual ryegrass, for instance, that when you include PGPR with the seed, that you get quite a bit better tolerance to higher levels of chloride or produced water, and the seed will germinate Same with perennial ryegrass, tall fescue, and tall wheatgrass. And then you can look at the averages here. So you can see that the PGPR provides quite an advantage to the germination of seeds in produced water. And the box will just give you a percent in how much it's increased. Mean germination time, we actually want the mean germination time to decrease because we want the seeds to germinate faster. And when you look, once again, comparing the hatched control boxes, which are untreated, to the treated ones, and there's two different chloride concentrations on this particular chart, you can see that including a PGPR or CMH3, the one that we're working with, you can actually decrease the germination time. So that means that the seeds that are there are able to germinate faster. And then if you look at percent germination, or how many of the seeds in the plate actually manage to send out a root or a shoot, once again, we want the amount of germination to increase. So when you compare to the untreated control, you want to see the numbers go up. And you can see it with annual ryegrass, when you're working with a more stressful situation or the higher chloride concentrations, that you will get increased germination when the PGPR are present. So what happens when we look at trying to increase that even more? And we know that the plants are limited in their capacity to take up sodium and chloride. So can we increase the biomass? Because by increasing the biomass, of course, we can increase the remediation if we're working with soils. So improved germination should lead to better growth and better biomass amounts in the field. So the first one we looked at was gibberellin, which is a plant hormone, and it regulates germination and stem elongation. So it should break seed dormancy, and hopefully in the presence of gibberellin, then there should be better germination, and the seeds should be more tolerant to produced water. If we look at the LC50s, once again, the hatch box is the untreated control. We're comparing to that treated with just PGPR, that treated with gibberellin alone, and then that treated in a combination of CMH3 and gibberellin. Just a reminder, we want to see an increase in the chloride concentrations, or the bars get bigger, to show that the seed is more tolerant to the concentrations of produced water. So it's got a higher concentration for 50% lethality. So it looks like in some seed types there might be a bit of an advantage, such as with tall fescue here. But when you look at the overall numbers, there seems to be no real advantage with the LC50 values of adding in a plant hormone like gibberellin. And then you can also see that when you look at the percent germination, and I picked a particular chloride concentration when I did this, you can see that when you look at the averages overall, that there is no advantage to either replacing CMH3 with a gibberellin or adding it in combination. So, same with mean growth time. It doesn't make any difference to include gibberellin. What happens if we look at another plant hormone called tryptophan, and this particular one is a precursor to IA plant hormone, so it's naturally present. So if we can increase in the amount of the soil, do we increase the plant growth associated with that? So once again, when we look at the LC50s, we're looking for an increase in the chloride concentration associated with a particular treatment, which shows that the seed is more resistant. And when you look at tryptophan in combination with CMH3 compared to CMH3 on its own, there is no advantage in either of the produced waters. You look at the percent germination overall, you can see once again that the tryptophan really didn't do anything more than the PGPR does. And same for mean germination time, although we did get a bit of an advantage with including tryptophan in the mean germination time. But when you look at percentage germination and the lethality results, it's really not enough of an advantage to increase the expense of adding it in. The other thing we can do is look at other PGPRs to see if there's something that's better than what we already use. And so when we're looking for bacteria from contaminated soil, we'll culture them and then we'll look for interesting morphologies or interesting colors. For instance, this particular one is red. You can see that once it's concentrated. And this particular one has an interesting morphology, actually forms a biofilm. So when we look at doing the same types of germination studies in the presence of produced water, what effect do we have on the LC50 values for those? And there's two isolates here that we looked at, I3 and an SR, and we compared it to our existing bacteria, CMH3. Once again, the hatch foxes are the untreated control. So we want to see an increase in the concentration of the LC50 when we do our treatment. And you can see that when we look at the other bacteria compared to what we're already using in either of the produced waters, we don't see that there's any benefit to switching up from the bacteria that we already used. When we're looking at percent germination, you also see there's no real advantage. And same with mean germination time. There's no real advantage here over what we're already using. However, the SR bacteria that we've been working with has a different mechanism of action. So we're going to do some additional studies with this going forward, using it in combination with CMH3, because it's possible with the different mechanisms of action, we may actually still get an enhanced benefit to germination. So those studies are going to be upcoming. We have done field work. I've showed this data before if you've seen any of the phytoremediation talks. This is some field data from a project in southern Saskatchewan. And the idea was, could we use PGPR to revegetate a grassland site that was really struggling to get revegetated and treated in other ways? So the goal was to revegetate, but also to reduce soil salt levels. And in this particular case, the 4 seed types we were using was annual ryegrass, perennial ryegrass, oats, and tall wheatgrass. And that's a particular PGPR we were using. So this is what that site looked like. You have these bare areas that had real problems getting any kind of vegetation. They were using other methods here to try and eliminate this sodium and chloride problems from the soil. When we used a PGPR treated seed, you can see how quickly we were able to get vegetation reestablished on that site. And then after year 2, you can see that the growth is still really good. Just a note on when you're working with plant species to remediate salt from soil, because the plant takes up the salt, you actually have to remove the plants from the site in order to remove the salt from the site. So those plants on this particular site are harvested like any other agricultural crop, and then that material is removed from the site, and that results in a reduction of salt in the soil. And when you're looking at trying to predict how these plants will work with salt remediation, this is what we're seeing: an annual decrease of 1 to 2 decimeters or decisiemens per meter. As I mentioned, this is the uptake, 65 grams per kilogram of dry mass, and up to 150 kilograms per hectare for the biomass productions we currently get. So of course, as I mentioned, the goal for us is to try and increase biomass productions. So far, we've had limited success with that. We're working on some combinations of things and some other bacteria, and we're going to see if we can get that up even more. One of the other things we've been doing is some reclamation studies in the laboratory using a salt-contaminated soil, and that's the parameters for this particular soil. The EC is around 17, SAR is around 18, and the soil came from a particular site in Saskatchewan where they are having difficulty revegetating. So this is what we were working with. We had blue grama grass plugs, and these came as you see them there. What we did is we placed those glass plugs in salt-contaminated soil in the laboratory, and we added PGPR in a solution directly to the plugs as we planted them. So this is we had a control set. We had 2 mils of PGPR in one set and 10 mils of PGPR in the other. We did not fertilize these pots, and we were watering with a tap water to maintain the concentration of the water at around 60%. These pots do not lose their salt with watering because they do not have holes in the bottom. So we looked at this growth for a period of 7 weeks. And if you look at the results for median height, you can see that compared to the control and the lower volume of PGPR that was added, you get quite a significant advantage to the plant height when you treat with PGPR, when you plant these plugs. You can see these graphs on the right-hand side, that shows the range in height of the plant. So you can see there's quite a bit of a larger or a maximum height that you can see with these plugs that were treated with PGPR. This is what these plugs look like by day 33. We had better growth in the 10 mil PGPR trial, as the height graph showed. So this is what we chose to use when we went forward with a small field trial. And we did also do some work with L-tryptophan in these particular pots. They also showed no effect or no advantage to including that particular plant hormone. So these are some preliminary field trial results. We're looking at max height and medium height. So the light colored boxes are the max, the dark colored boxes are the medium, and you want to compare the treated to the controls. And there's 3 different sites that we looked at with 3 to 4 plugs per site. And what we saw is that the treated samples did show what we saw in the lab, an increased height in the plants. Also the medium height and the maximum height. So you can see treatment does result in an advantage to plant growth with this particular field trial with these plugs. And that's an example of what those plugs look like. Like I mentioned, it was a small trial. It's kind of hard to see them there. But when we were doing an observational evaluation on the health of these plugs, we found that once again, those that were treated with PGPR looked to be in much better health and had a better growth overall than compared to the control or untreated samples. So like I said, this was a preliminary field trial. We're going to be doing more work with this and try and expand this. This happened to be a site that had uncontaminated soil. It was a reclamation site. So hopefully we'll be able to find some salt contaminated sites and have a look again with PGPR treatment of plugs. So next steps for us, we're going to be doing some additional lab studies with PGPR, mostly in combination, and look at how the seeds respond to the presence of salinity. Just one more slide here. And then we're going to look at some growth pouch studies and then do some more field deployment work and some additional lab studies. The other thing we're working with is some flowering species. So this is some pictures from one of our reclamation sites here in the city of Calgary. And we're looking at whether we can use PGPR to get some wildflowers established on sites in addition to some native grasses. So we'll talk more about that at another time. So I just want to thank the National Research Council. Their Industrial Research Assistance Program has funded a lot of this work. And we also want to thank the clients who've allowed Earthmaster to conduct the field trials to advance our PEP systems technology. All right. I am open for questions.
Okay, great. Thank you, Elizabeth. That was a great presentation. And we do have time for a few questions. We have a couple of minutes. There was a little bit of maybe audio visual, and I can't tell if it's just on my end, perhaps an issue with my internet, or I missed the last slide of audio when you were presenting. I'm just monitoring the questions here. If you have any questions, please feel free to type them. In the meantime, I have a question for you, Elizabeth, in some of the different types of applications, and my apologies if I missed that in the last slide. What kind of sites have you applied these to?
So most of the work that we've done so far has been hydrocarbon contamination and a little bit of salt contamination. PEP Systems is very effective at hydrocarbon remediation. So if anyone's seen any of the previous talks, it's especially well suited to remote and hard to access sites. And it's quite effective at removing all types of hydrocarbons, the heavy-ended hydrocarbons that are particularly difficult to treat. It's effective at treating salt remediation. The problem with salt remediation is that it takes quite a bit of time to remediate salt, and clients generally want something that's a bit more effective than that. Hence the laboratory work that we've been doing to try and increase the biomass, because of course if you can increase biomass production, you can increase the rate of salt remediation. The reclamation studies, those are at the trial stage. We've been working with a variety of wildflowers, some native grasses, some of the more traditional PEP systems grasses. We're looking at sites that are difficult to get revegetated. Generally, when you reclaim the site, you don't have a lot of topsoil, so we're working with subsoil. So anything that we can do that will give a better chance to the reclamation species taking hold, then that's really what we're focusing on right now.
Great, thank you very much. I think we can move on to our next presentation. That will be presented by Kevin French. He is a Vice President at Vertex Environmental, and he will talk to us about an application of activated carbon. Kevin.
Okay, thank you, Parisa. Can you see my screen and myself okay?
Yes, excellent.
We'll assume we can. Okay. Thank you, everybody, for joining us here this afternoon virtually in the comfort of your own homes. Today, I'm going to talk about what I think is a new, fairly exciting, sustainable remedial technology that can facilitate risk management and closure of mobile NAPL sites. This is a nice extension from the earlier talk that Jean gave on activated carbon amendments. My name is Kevin French. As I said, I work for Vertex Environmental. Bit of background on myself. I'm a UW grad with about 30 years of experience in consulting and contracting. Vertex is a specialized environmental remediation contracting firm that offers in situ and ex situ treatment systems, high resolution site characterization. This is just an overview of some of our services, but I wanted just to point out this one here. We do have an in-house laboratory where we complete a lot of our own bench scale testing activities, and this was a direct benefit for us taking on the work towards developing this new technology. An overview of the presentation here, which I won't dwell on because we're going to get right into it. So in terms of applicability, what am I talking about? So this technology is applicable to LNAPL, and in particular, we're talking about petroleum hydrocarbon LNAPL. So everything from measurable thicknesses, like you see here, centimeters, meters of product potentially, as well as thin films and even down to petroleum hydrocarbon sheens. We're looking specifically at mobile or migrating NAPL, not residual NAPL that's bound up in the formation, but NAPL that is available and extractable from the ground or otherwise could migrate. We're looking at a technology that doesn't involve physical removal or destruction of the NAPL. And that's important from a risk perspective if the presence of the NAPL itself isn't causing an unacceptable risk and it doesn't require removal to counteract that risk. And also, in certain situations, removal is not possible or even desired. For example, if there's no coincident excavation planned where you can take advantage of that to remove NAPL, or in the situations where it might be too deep or beneath a structure like a building or a road or down into the bedrock, it can be very, very costly to physically remove or extract NAPL from the subsurface. There's a variety of approaches that could be used traditionally to deal with NAPL impacts. Removal and destruction, there's a series here, so physical and systems types of removal of NAPL from the subsurface. There's control and management techniques as well, and obviously combinations of all of these. The technology that I'm talking about today is essentially a combination of these two, adsorption and permeability reduction. Risk assessment challenges. So please give me some slack here. I'm not a risk assessor, so don't judge me too harshly, but my understanding of how different jurisdictions in Canada deal with risk assessments relating to petroleum hydrocarbons and NAPL in particular are summarized here. So in BC, there is a requirement to assess whether the NAPL is mobile or whether it's stable. So this typically involves a long monitoring program. If it is mobile and it shows up in wells, for example, this can trigger a high risk site classification, which is very problematic. And also, depending on the constituents of the NAPL, could have vapor intrusion considerations. In Alberta as well, you have to assess whether the NAPL in the source area is mobile or not, whether the source itself is stable and decreasing or not. And if it's not, you have to do some active management and remove it to the extent practicable. You also may require additional exposure controls and risk management measures. In Ontario, NAPL is permitted under a risk assessment if it's in the bedrock, but it's not preferred if it's in the overburden. We see this language again to remove it to the extent practicable, and that includes everything down to films and sheens. And there's also a provision in Ontario where if you have concentrations that are in excess of 50% of the solubility, you have to demonstrate that there isn't a potential for an apple to form in the future. You also have to look at vapor intrusion considerations. So we asked ourselves, what if there was a way to effectively immobilize an apple in situ to allow easier approval of a risk assessment? This could be very beneficial. It could assist with reducing offsite risk, need for barrier walls, for example. It could address a groundwater to surface water migration pathway that could be problematic, reduce vapor concerns, and also dramatically shorten the length of monitoring programs. So we came up with this block and absorb technology. The concept behind it is bind the NAPL in high concentrations of petroleum hydrocarbons in soil and groundwater, lower the formation permeability, and enhance the potential for biodegradation to take place over the longer term. Block essentially is Portland cement, adsorb activated carbon. So let's look at this scenario. You have a site with a risk assessment that's been completed. The soil and groundwater concentrations themselves pass the risk assessment, so they don't pose an unacceptable risk. But under the local jurisdiction or the risk assessment guidance, mobile NAPL's not allowed because then there's a concern over a possible migration of that NAPL. With a block and absorb type solution, we'd be looking at immobilizing the NAPL in situ. Ideally, it wouldn't be limited to depth of the NAPL, whether it's a buffer below the water table. It wouldn't generate wastes requiring unnecessary excavation offsite disposal or other types of treatment. So we took this concept into our laboratory and completed a series of bench scale testing activities. 2 stages were undertaken. First stage, we looked at the blocking capacity of Portland cement alone in reducing formation permeability and the adsorptive capacity of GAC alone in soils to absorb the hydrocarbons. And then we looked at combining them in different concentrations and proportions to make an assessment of whether there's any synergistic benefits of using them in combination that might make the technology more effective and less costly. For this particular site, we were working with Waterfront Toronto on the Portland redevelopment project. So we obtained some representative soil samples from that property. We completed baseline testing on the samples for presence of NAPL as well as bulk concentrations of hydrocarbons. And in some cases, the soils weren't actually contaminated enough for our purposes, so we ended up spiking them with hydrocarbons to bring the concentration up to about 30,000 parts per million. Before and after treatment, we looked at a variety of factors of the soils. We looked at hydraulic conductivity. We looked at the presence of NAPL or sheens and whether it was mobile or not, and we did this in a couple of ways. One, we looked at physically agitating the soils and seeing if we could liberate sheen or NAPL from them. And we also completed some flow-through column testing to see if we could liberate any sheens from the soils. We wanted to assess the effect of the treatment on the workability or the soil-like texture of the material because we didn't want to turn the subsurface into a block of concrete, which could have restrictions on its future use. And then we looked at concentrations after treatment, bulk again in the soils and also in the leachate. This is a graph of the permeability change with addition of GAC and Portland cement separately. So you can see the blue line at the top here, if you see my cursor, is the change in hydraulic conductivity when we added just GAC alone. Very little change. In fact, it went up slightly because of the grain size of the GAC we're using versus the soil texture. The Portland cement line here, you can see a nice logarithmic decrease in the hydraulic conductivity with increasing concentration of Portland cement. So a nice relationship there, which demonstrates the block action of the Portland cement is working. When we looked at combinations, we saw decreases as well when they're combined. So the slight increase in conductivity with GAC did not counter effect the decrease, which was more significant with the addition of Portland cement. So we're still seeing good reductions in the hydraulic conductivity when we apply these amendments together. This picture here is a series of jars where we did some agitation testing and moving from right to left, just to keep you on your toes instead of left to right. We have the higher concentrations, so the control samples here. The top row is increasing concentrations of Portland cement. In the bottom row is increasing concentrations of GAC. And we added a dye, an oleophilic dye here, so that we could see the NAPL more clearly. And you can see as you increase the concentrations of both, you get significant reductions in the amount of NAPL that was able to be liberated out of these soil samples. When we look at this, a different way of graphing up the data, you can see here GAC alone, the degree of NAPL being removed from those samples decreases qualitatively as you increase. Same with Portland cement, you see this decrease as you increase the concentrations. But this is interesting, when you combine the two, you can see right away, any combination that we tried of the two together, we didn't see any NAPL that was able to be liberated from these samples. So this is a pretty drastic illustration of the synergistic benefit of combining these technologies, where you need fairly large amounts of GAC or Portland cement alone, but very little in combination to completely eliminate the mobilization of NAPL from these soil samples. So this was a pretty interesting finding that together the relatively low concentrations are more effective than using even higher concentrations of Portland cement or GAC in the soils. We also looked at the concentration of hydrocarbons in the leachate that came out of our flow-through columns. And you can see the total hydrocarbon concentration here. As you increase concentrations of GAC in Portland cement, they drop off dramatically to the point where they're actually non-detect. And this was also a pretty important finding that we came to, is that above a certain concentration, the treatment would not only immobilize the NAPL, but it would essentially make the hydrocarbons unleachable in the groundwater. So that was a pretty interesting finding also. So just to sum up, the bench scale testing combined, it was more effective than individual when we add Portland cement and GAC. We could effectively immobilize NAPL and sheens in soils that had up to 30,000 parts per million. It still stayed soil-like in consistency up to certain moderate concentrations of Portland cement. And just low to moderate concentrations of cement decrease the permeability 80 to 95%. So with this treatment, we saw a significant reduction in the leachability, and with high concentrations, essentially unleachable concentration. So that was pretty impressive. And based on the amendments that we're using, we determined that it should be applicable to treat soils using this technology in an in situ type situation. So then we moved on to pilot scale testing. For this part of the program, we worked extensively with our partners WSP, and they were instrumental in a lot of the monitoring and sampling programs that took place as part of it. But we moved out to the waterfront site in Toronto, and we did some site characterization work. We found an area of the site that had very high concentrations of petroleum hydrocarbons and NAPL present. The concentration in the soil on average was about 45,000 parts per million, so very high. We constructed 3 test plots, a control, and then 2 plots where we looked at different methods of introducing the amendments into the subsurface, so a soil mixing approach and a direct injection approach. Then we monitored these blocks over a period of weeks, sampled them, checked for NAPL presence, and analyzed the data at the end of that 8-week period. So the 3 plots that we looked at, control plot, obviously we didn't do anything to this, it was left undisturbed. We didn't add any amendments or introduce any other changes. The soil mixing plot, the amendments were introduced by direct placement, followed by soil mixing using just standard excavation equipment. For the injection plot, we mixed the amendments into suspensions and slurries and then injected them using direct push drill rig and injection pumps. So here are some photos of the soil mixing plot. You can see the excavator here. We're just stripping off the surface soils to get down to the water table. Once we get down to the water table, you can see the groundwater and NAPL came pouring into this. Here's a close-up view of the excavator bucket. So this is a pretty nasty area, a lot of product that's mobile that shows up in the excavation. So the first step was the addition of the GAC. This was added in bulk, mixed in with the excavator through the impacted zone. So above and below the water table to take account of that smear zone. Then Portland cement was added similarly, and mixed through until we got a good consistent mixture that was fairly homogeneous. And then the area was backfilled and a monitoring well was installed for ongoing monitoring. Just to show you what it looked like before and after again. So here's what the excavation looked like when we open it up. You can see the dark brown napple here. Afterwards, much more uniform, dried out, doesn't look visibly that contaminated. For the injection plot, we use PAC instead of GAC just because it's easier to inject. We mixed it up in this custom-built injection trailer of ours to inject it in a suspension into the subsurface. And then the Portland cement was mixed up in a slurry using this grout plant and also injected using direct push. This is a little more challenging to introduce the amendments this way and get uniform distribution because you want that so you get contact between the remedial amendments and the contaminants. So if you look at it in profile view with the drill rig here, we try to inject vertically in a series of interlocking vertical short distances that then try to distribute the amendment as uniformly as possible vertically from point to point on a grid basis. In plan view, ideally, this is what you want to do, a fairly tightly spaced grid with overlapping ROIs. And when you inject in this manner, you effectively minimize the degree of the effect of subsurface heterogeneities on the movement of the amendments in the subsurface. After the treatment took place and the monitoring wells were reinstalled, there was some monitoring that took place. You can see here on the left, this is the control plot. Clearly there's NAPL that shows up in that well, which is what you'd expect if it's mobile. The center one here, this is pretty dramatic. This is the soil mixing plot, and you can see the baler, it's perfectly clear. There's no oil on it, so clearly effective in immobilizing the NAPL in that one. This is the injection plot, not as successful. You can see there's NAPL in this well, and I'll explain that shortly. After the 8-week monitoring period, we went back to the site with an excavator and we opened up the treated soils just to do a visual inspection to see what was actually happening in the subsurface and what the effect of the mixing and the treatment looked like. So here's the excavation plot. You can see within the treatment zone here, it's fairly uniform. The soil looks good. When we excavated slightly outside of it, you can see the same conditions here. A lot of NAPL on the surface of the water table, freely mobile. So a pretty dramatic demonstration of the effectiveness of this technology. For the injection plot, it's a little more difficult to see. I'm sorry about that, but you can see it's a little more heterogeneous, variable in the subsurface here. I always have trouble with that word. And it's a little blocky. You can see streaks of GAC. You can see chunks of Portland cement. So not completely as nicely uniform the distribution as we would have liked. But then again, not that bad, but once you step outside of the treatment zone, you can see again, NAPL comes pouring into that excavation from the surrounding area. The soils itself that were treated looked fairly similar. Where we had good distribution, you can see on the left here, this is the soil mixing plot, and on the right, the injection plot. The soils became more cohesive. They didn't look that visibly contaminated. And the NAPL was bound up in the interior of this mass, but it was still easily excavated and behaved, and was friable, so behaved more or less still like soil. Now, just to refresh your memory, we're looking at 45,000 ppm in the soil here in both plots. This is a graph showing NAPL recharge into the wells over the 8-week monitoring period post-treatment. This blue line here is the control plot, and you can see, there was NAPL a couple centimeters per day that showed up in that well. It bounces around. You can still see it showing up here. So once well stabilized, it's still producing NAPL. This greenish line here is the soil mixing plot, and you can see post-treatment here, NAPL was non-detect in that well for the entire 8-week period, which was very promising to see. So it completely eliminated the NAPL from showing up in the treated soil. The red graph here is the plot of NAPL recharge in the plot that had the injection approach. And you can see after injection here, There was a few weeks where there was no NAPL in the well, and then it starts to rebound and we get NAPL showing back in here. And the reason for this is we figured with a single injection event, we had limitations on the massive amendment we could introduce into the subsurface. And it likely wasn't enough to overcome this 45,000 level starting concentration. We probably would have had to do 2 or 3 applications of the treatment in order to get enough mass in through that injection approach. So the main findings from the pilot scale testing: the block and absorb proved effective at immobilizing LNAPL in the field in situ. Each of the delivery methods was suitable for delivering and distributing the remedial amendments in the subsurface. Soil mixing obviously was better at homogenizing the soils and ensuring a uniform distribution of those amendments. And it would be suitable for near surface soils in areas that were also amenable to physical disturbance. The injection approach wasn't as good as distributing those soils, those amendments through the soil. So either a tighter spacing and probably a higher loading would have been required to fully immobilize the NAPL. But that approach shows promise as being suitable for deeper soils or areas that aren't amenable to physical disturbance, or for example, under buildings or roads. And both application methods are designed to overcome heterogeneities. Like I said, the soil mixing approach directly overcomes it by homogenizing the soil. The injection approach, you have to be very careful on your distribution, your spacing vertically and horizontally in the injections to make sure that you get as uniform a distribution as possible. And also we saw the similar results in the pilot as we did at the bench, where the dissolved phase groundwater concentrations of petroleum hydrocarbons were reduced by upwards of over 90%. So overall conclusions, we go back to this premise: what if there was a way we could effectively immobilize NAPL in situ to allow easier approval of a risk assessment? With this technology, we demonstrate that you could treat NAPL without excavation or mass removal or destruction. With the soil mixing approach, we could mobilize at least up to 45,000 milligrams per kilogram of F2, F3 range hydrocarbons, which is pretty significant contamination. And we estimate 15 to 20,000 with one injection event using the injection approach. So if you had higher than that, you might have to add another amendment like an organoclay, or you might have to do multiple injections to get that mass in the ground to overcome those limitations of that distribution technology. Drastically reduces dissolved phased petroleum hydrocarbons in the groundwater as well, and doesn't generate any waste. Relatively low cost, and because of the approach of the technology without removing anything, it's a sustainable solution. Next steps for this technology: there needs to be some additional assessment done on the mobility of NAPL from those treated soils. For example, at the waterfront, they did frozen core residual saturation testing. Obviously, some longer term assessments are needed. The durability of this treatment to sustain NAPL immobilization, whether it's applicable to other contaminants as well, if that's possible, and other stratigraphies, so cohesive formations or bedrock, and what the effect of it is on vapor suppression from more volatile constituents in the NAPL. Further field trials obviously are needed. And then finally, assessment of whether this approach is going to be acceptable under risk assessment guidance from the regulatory bodies. It is acceptable, I can tell you, in Ontario from a regulatory perspective as a treatment technology. So it's really just the acceptance from a risk assessment perspective that is something that needs to be evaluated a bit further. I would just like to thank quickly WSP, our technical partner on this. Obviously, I mentioned our client was Waterfront Toronto. Their partners, City of Toronto and Toronto and Region Conservation Authority, and funding that was provided for this by Federation of Canadian Municipalities. And with that, I am done, and I will be happy to answer any questions that there may be.
Thank you, Kevin. It's a great presentation. And we do have a few questions on this, and perhaps if there is time, we can go back to questions that were addressed previously. This one for now, a question from Ada Wang asking, what is the cost range for the AC application?
Okay, the cost range, yeah, it's going to be highly variable because it will depend on your site and the degree of contamination that is present. When we did our original evaluation, we estimated that with a soil mixing approach, you could be looking at an all-in cost of anywhere from $90 to $100, maybe up to over $200, depending on the degree of contamination. Like I said, the injection approach is a bit more expensive. You're probably looking at $100, $120 up to maybe $200 or $300, and that's per cubic meter of soil treated as all-in cost. So that's amendments, contractors, equipment, labor, things like that.
Okay, thank you. And we have another question, I think is related to the next steps that you mentioned in terms of long-term monitoring or potential for VI assessment. So the question is there any concern of desorption?
Yeah, it's a good question. It's something that obviously needs to be evaluated because this was only an 8-week trial. But I would say that if you look at the individual components of the technology, carbon itself is inorganic. It's going to remain in the subsurface in perpetuity, essentially. Portland cement is the main constituent of concrete, which again is durable in the subsurface for decades. So the components are very durable, and it would be important to make sure that the mass of hydrocarbons is accounted for when the design is done, so that initially there's enough activated carbon added to the subsurface to account for that mass and minimize or eliminate the risk of desorption in the future. But with the combination of the two and the synergies that we see, it's not reliant just on the carbon alone. The reduction of porosity with the Portland cement also really reduces the amount of flow through groundwater through that treated mass and potential for desorbing those contaminants.
Okay, great. I have another related question to that is, and I'm not sure if this is for Jean-Pierre as well as for you, and if the contaminants stay in the activated carbon, if it's considered as a secondary source. Kevin, I'll let you go first, please.
It's a good question. I think it depends on how you define source. Obviously, the testing that we did before and after treatment showed that the bulk concentration of hydrocarbons in the soil doesn't change. It's still there because we're not removing it. So if you're talking about a mass of hydrocarbon in the subsurface being a source, then yes, it still is a source. But if you're talking about a source in terms of its ability to liberate or the petroleum, allow it to migrate, allow it to desorb into the groundwater and migrate, I don't think it would be considered a source, because the objective is to immobilize that that contamination and prevent it from going anywhere, and therefore prevent it from exposure routes.
And Jean, would you like to add to that? If you're online and unmuted. I suppose this would be considered a containment type technology. You did mention that there is still potential for biodegradation when the contaminants are petroleum, hydrocarbon. Perhaps you need longer term data in order to assess that.
Absolutely.
So,
yeah.
Just to comment on what Kevin has said, if you have, considered the contaminant that is sorbed within the carbon matrix, okay, and you're sampling that carbon and having it analyzed with the soil, it could release with the hexane, in the lab, it would release some of the contamination. So it is contaminated soil. So in the example that Kevin was describing here, the objective is to reduce the NAPL mobility. It's not to remove the NAPL from the soil or destroy it. In the same way and manner, what I've explained on my presentation touching the use of the activated carbon, it's there to retard the movement of that hydrocarbon and to get it treated as it's dissolving from the soil matrix, or as it's intersected from the groundwater and come into the matrix of the carbon itself. So you have to have a proper way of treatment in order to get it degraded. Because, and I'll take BTEX for an example. If you have a very high contamination of BTEX in the groundwater, at one point in time you could typically build up enough in the carbon that your soil become contaminated. So that's why you need that treatment pathway to be possible. So that's my answer. I'm not sure if Kevin concurs, but that's my view on it.
Okay, thank you very much. So we're at 2 p.m. It is time for the break, but we also do have some questions for those of you who are interested to stay behind for Elizabeth Murray on the phytotechnology. So Elizabeth, would it be okay to ask those questions now?
Yeah.
Okay, great. So there's a question from Jeff Blanchard asking, have you used this technology in wetland sites, and how does harvesting look in wetland systems?
So we have done a little bit of work in wetland a couple of years ago. It's something we want to pursue more of. Obviously, it's a challenge if you're going to harvest in a wetland. So if it's a permanent wetland, you're not going to be able to. But if it's something that does have dry periods, then we would be able to harvest. Does that answer the question?
Great. I think the attendees are muted, so I'm assuming that answers the question. And there's a related one from Sherry. How does it disposal of the harvested plants from the wayborns?
You cut out there for a bit, but I think the question was what happens with the harvested material when we remove it from the site? It's got very low levels of, it's got non-toxic levels of salt in it. So it could be used for anything off the site. We tend to dispose of it because the clients that we remediate salt for don't want that material used for anything related to livestock or anything like that. Mostly from a perception issue. If you were to feed that grass to a cow and the cow died for some other completely unrelated reason, it's going to get associated back with the grasses. So we tend to dispose of it, or it's a popular item for the truckers that line their boxes to keep stuff from sticking to it. So it often gets used in that way as well.
Okay, great. And maybe just one more question, and this is from Joanne West asking, what depth of contamination are you targeting?
Sorry, can you repeat that? You cut out.
Okay. Sure, that's from a question from Joanne West on what depth of contamination are you targeting?
So the depth is restricted to the rooting depth of the plant. So with the species that we work with, it's generally around 1 meter. If you have deeper contamination, generally what we'll do is we'll dig up the soil, place it on a level surface, and then we'll farm it as you do any other kind of agricultural plant. So we will build a containment system and place the contaminated soil on that and farm it. So the contamination can be remediated down to about 1 meter in a growing season. So if it's more soil than that, then we'll treat the upper layer, strip it off, and then replant the layer underneath, treat that, and then so on until the whole thickness gets treated.
Okay, great. Thank you. I think we can take maybe a few minutes break for everyone and come back at 10 past for the remainder of the
Well, thank you, Parisa.
SNC-Lavalin was founded in 1911. We are a leading engineering and professional services group with over 40,000 people around the world. Our Environment and Geoscience group has one of the most comprehensive environmental consulting teams in Canada. Our experience includes conducting thousands of projects across multiple industries, including retail and manufacturing, oil and gas, utilities, mining, transportation, chemical and metal processing, and land development. From concept to closure, we have experience spanning the entire project lifecycle and decades of experience with the environmental regulatory system. Our teams seek innovative solutions to quantify, reduce, or remove environmental risks and liabilities. We help clients with environmental site assessments, risk assessments, remedial options analysis and action plans, remediation and reclamation, risk management plans, hydrogeology, groundwater modeling, as well as expert review and litigation support. As an organization, we are committed to being a corporate citizen and active in the communities in which we operate. Talk to one of our consultants to learn more about our unique environmental solutions.
Hi, Kevin. Are you online?
Hello, Parisha.
Oh, hello.
Okay, I got Daryl here on the phone anyway.
Oh, okay, excellent. It is working.
Robert should have control of our screen, I presume.
I'm
So-
here. I am not able to share the my screen. It's waiting to view your screen, so it needs to
Okay.
be pointed to me as a presenter. Oh, there we
Okay.
are. Winner.
Okay, I think it's 2:10 and I think we can restart.
Okay.
Thank you, everyone. All the attendees and the presenters. This is a great session and we're going to continue our talks with a presentation by Robert Hobbs from Aegis on thermal desorption, and Daryl Greenman, who is traveling at the moment, was able to connect, and he will provide an intro for us. Daryl.
Thank you very much for the introduction. First of all, good afternoon, everyone. I also want to take a minute from the Aegis team, Robert and myself, to thank Joe and the team for all the work involved in maintaining this incredible annual event, just in a, unfortunately, different format this year. But we're all learning to pivot and make new gains in new ways. So I am having a connectivity issue, so I'm phoning in. Just going to make a brief introduction to the company, and then Robert will walk you through the PowerPoint. But I certainly want to make myself available as possible. And following the presentation, I'm a phone call away, email away, and happy to talk. So as a founder of Aegis, this little adventure began simply as an avenue to make change and lead ourselves and perhaps even drive others to find some betterment in how we deal with waste and the solids component of what I feel is our environmental obligations. The goal is simply to define thermal desorption, which over the course of 30 years to some has been a four-letter word, but we simply had the expectation of, complete recovery along with many other things from what is called waste in our industrial terminology, and we looked at it as an opportunity for value. So we set out to have absolutely no incineration, no oxidization, zero fugitive emissions, the ability to spread clean solids in situ in the allowable cases, and to create an upgraded saleable BS&W quality oil with our 99% recovery. We help the industry remove liability and land and leaching problems. So we begun, in the early years of this, a few years back, with the obvious engineering, modeling, bench testing, and some processing via small 100-pound per hour unit. By the end of 2018, we had a commercial grade unit operating within our own location with a throughput of 4 to 5 ton. And we simply spent several months testing, trialing, and learning our technology as a whole. This moved up to discussions with multiple groups. And by late 2019, we had an industry partner in Tervita, and we continued to do so through 2020. As of late, we've actually had processing with Service Synovus as well. We've processed essentially anything in terms of waste stream that Tervita deals with immense success, and often have exceeded not only our expectations but theirs. And this was similar results with Synovus and all third-party validation. And with Synovus specifically, we are dealing with their centrifuge paste issues and all the costs associated. So the technology itself is a true low-temp indirect electrical heat-based process. It's a fully closed-loop system that recovers all hydrocarbons and upgrades it to that saleable grade hydrocarbon product with low impact, low decibel, and again, low temp processing. We simply vaporize, capture it, cool it, condense it, and upgrade it. This oil can be made suitable for in situ disposal, and in necessary cases, just made more suitable for, non-hazardous disposal, which is a great cost savings amongst other things. So we do achieve less than 5 milligrams per kilogram concentration of hydrocarbons on the outward end of the feedstock. We are portable. Certainly, we do suggest running off the grid power source to achieve the highest return for your bottom line. We have proven ROIs between 1 and 3 years, of course, dependent on the values within your waste stream. Again, lots of third-party testing, validation outside the industry partners. And we've also founded, other options are, 2.5 times more expensive, 50% slower, produce a lower quality oil product, and a lower quality soils residual at the end of the phase. We do carry extensive IP. We've continually added and grown on that. As of late, adding plastics to the processing, which we had great results in, and able to utilize essentially 100% of the waste for other avenues. But again, that's a little more of a focus down the road. Now, certainly, as far as the elephant in the room, we've all had to deal with this COVID problem. And that's simply how we looked at it. We were just forced to deal with a different way to do it. And like everyone, we slowed down a little bit, but got back on track real quickly, and allows us to maintain our commitment as a corporation to stewards in the attack of, in our attack on the solid waste industry, with the objectives being, for the benefit of the environment, we obviously need to have a value proposition and create a great value, financial return, cost savings, and certainly liability mitigation, which most every group and individual often forgets. We knew to be a differentiator, we had to have distinguishing characteristics to not only technology, but our culture and our plan as a whole, if we intended to lead the way. So through the industry partnership with Tervita, we have been able to continually enhance all aspects of technology, grow an impressive value-added recovery, and continually advance the technology itself. The bottom line is we get value from waste, and we garner significant cost reductions to end users through product recycle, reuse, and recovered value-added products, with, again, the reminder of liability reductions. Not to be limited to the capabilities, but we have successfully shown waste volume reduction, toxicity reduction, improved waste handling, and certainly disposal costs, and beyond a reasonable doubt, greenhouse gas emission reduction from start to finish in this application. Other than that, there is a really nice presentation we've recently put together. I'll close my intro and hand this over to Robert. But certainly following the window of time we have today, and perhaps easier for some, simply a phone call away or an email, and happy to sit down over coffee, come to you, meet up, or simply get on the phone. So at that, I'll pass it back to you, Robert, and take it away, my friend.
Thanks, Daryl. This is going to be a little different from some of the other presentations. Not that we are departing from that, but Aegis is in a different position as a kind of an upstart technological company solving some really important problems. We wanted to focus on results and outcomes from the business side as much as from the technology side. And as Daryl very clearly put it, the technology, while not new, has for a long time been around, but has kind of struggled to find its footing. And Aegis and the thermal trap system have really taken that struggle and found a way to give it that footing. And I want to talk to you about how producers, remediators, and consultants can generate value from the waste stream, because that was the mission of Aegis right from the beginning. And that is what thermal trap does, is it turns, as Daryl said, it turns a waste stream into a revenue stream. And we all know that oil prices are pretty beat up right now. Don't have to tell anybody that. But it can also offset costs, even at low oil prices. And anytime you can reduce operating costs, well, that's a pretty good story to be telling, not only to industry, but to government and to everyone who has a seat at the table or eyes on the prize. So let's get into what Aegis thermal trap is really about. The issue here for thermal trap is one set of simple questions, and that is, can waste remediation technology really help a company to elevate its environmental leadership, to cut its costs, and ultimately boost the bottom line? Now, obviously, we know that the answer is yes, but I think what's really important is why it's yes. The yes that comes from Aegis thermal trap is because from the very beginning, we built into the system the intent that it was not just about turning out clean soil, processing centrifuge paste. It wasn't only focused on those things, but it had to be focused on making business sense. One of the big things, and we'll talk about this a little more in this presentation, one of the big things holding industry back from achieving truly unparalleled levels of environmental responsibility was the cost. So we knew it was a big deal. We knew something had to be done about it. And with all the eyes on the industry, and especially in Alberta, we knew that this had to be absolutely unequaled in terms of its ability to not only elevate the environmental leadership, to cut costs, and as oil prices continue to rise, to give a significant boost to the bottom line. Why? Well, it's pretty obvious. This is not something that any of us are going to come to as a surprise. Soil contamination by petroleum hydrocarbons results in significant human health, plant life, animal, and environmental defects with rising public concerns. And that is what I really want to make sure everybody remembers, is that the public is watching. This is a big topic on everybody's minds. And we as remediators, we as waste managers are the front line for things that typically nobody has seen in the past. And it's really imperative that we give industry the tools to show up the way they need to show up. Studies of industrial companies, actually all companies, but it's very focused on industrials and how we show up in the world, show a negative reputation reduces or significantly hampers revenue and ultimately investment. Positive reputation, of course, by corollary, boosts the bottom line and reduces negative revenue impacts. Now, what do I mean by that? I mean, when things go wrong, and we know they always go wrong, when you have a good reputation out in the world, amongst your investors, amongst your customers, amongst the general public, when things do go wrong, you're going to be less susceptible to the kind of problems and backlash. That is a big deal. That is a huge deal. And a remediation technology that can give you the ability to boost your image as a business and shield you from problems, that's worth more than just the technology itself and just the cleaning of the soils and waste products. It's a direct contributor to the success and the health of a business, of your partnership with industry, of your partnership with waste management, and as a consultant or service provider, you become part of that increased value chain. Now, we're talking about reputation, we're talking about image. It's another elephant in the room, and that is the amount of attention that has been flooding into Alberta, into Canada, and into the oil industry in general. I just want to talk briefly about the oil sands themselves. I mean, we all know what's been going on. This has been going on for years now. Major oil sands projects canceled, protests, pipelines being shut down, despite being compliant. We've got environmental assessment times skyrocketing. We've got investors stepping away because they don't want to be involved in the tar sands or fossil fuels projects. And it's being concentrated in Canada and in Alberta. Time and time again, it's clear, compliance isn't enough. We have a black eye in this business, not because we're doing anything wrong, because we're doing everything right, but it's being done in a way that kind of falls below the radar for years and then all of a sudden bubbles up. We know what's happening. We know what's going on. Greenhouse gas has become a household topic. When you've got people who are uninformed about what is actually happening, knee-jerk reactions happen. Governments, regulators, listen, they're all people too. They are just as susceptible to the problems and panic of the situation as the general public, as the uninformed general public. Although, as the increasingly informed, as more and more information streams come available to them from social media, from the broadcast media, which are often aimed at sensationalism rather than at accuracy. Now, we're not talking about fake news here. I don't even want to go there. But what we're talking about is the fact that most people, and we've all seen in the presentations that have preceded this, the amount of technical, industry, and expert knowledge required for most of these endeavors is significant. So how can we expect the general public, who is increasingly bombarded with soundbite level messages, to have any view other than the fact that this is a problem and let's point to where we think the biggest problem is? And we'll come to that in a moment. But for the industry itself, for us as remediators in waste management, and for producers and the consultants and the service providers in this industry, this has another implication. And I hinted at it before in that last slide, but that is that greenhouse gas is now an investment topic. Virtually every investment house that puts money into energy projects has either a specific group tasked with understanding the environmental impact, or they are part of an organization or a group of environmental impact assessors who, at the financial level, are looking at what is the reflection by the industry, by the by the public, and by other investors that they are then using to garner funds. What is the impact to them of an investor putting money into an energy project? And we are seeing increasingly that it is very, very detrimental. I want to talk about a specific group of statistics that are going to put this in very clear image. I want to talk about the energy project drain. In a 4-year window from 2014 to 2018, there was a massive decrease in project investment in Canada, 53%, to the tune of 150 billion in lost projects. Now, that doesn't even count some of the projects that were kind of put on hold, but not actually stopped, or that were slowed down, or things that never even got to the table, just ones that we know got shuttered because of, well, because of the reputation, because of the environmental impacts, because of the concern being raised at all levels, beginning with the public and stemming through to the investors. Now, before we look at this and say, well, of course, the oil industry was in major trouble during much of that time. And that's true. There were a lot of problems out there beginning in that period. But the impact was in Canada to a much greater extent than the rest of the world. In the United States, there was a 50% increase in project investment to the tune of 473 billion in new projects. And that does not, even factor in the projects that continued on, that weren't interrupted. It doesn't even look at any of those other aspects. And globally, likewise, there was a 36% increase in project investment during that period of time, to the tune of $254 billion. So clearly, something is happening in Canada, and primarily in Alberta, that has a massive, massive impact on our ability to operate as an industry. And that's, well, it's complicated, but it comes down to this. As the money pouring into the oil sands took investment away from, or displaced investment in conventional oil production, we saw two things happening very clearly. One, massive revenue generated, obviously a brilliant investment strategy during that period of time. But unfortunately, we, the industry, and I mean all levels of the industry, we functioned essentially in a bit of a vacuum, partially unaware of just how bad the public sentiment really was about oil. Now, there's been a lot of surveys about this. There's sources that compete with this information, but the bottom line over and over again is, as we invested at the surface with what are essentially open pit mines in the oil sands, the reputation of this industry, the reputation of the companies operating there, of Canada and of Alberta, was damaged. As I mentioned earlier about reputation, poor reputations expose you to problems. Good reputations shield you from problems. If the entire industry is, pardon my pun, tarred with the same brush, then what happens? It doesn't matter what the individual companies do if they are not standing out from that, they have a reputation and sentiment problem. As the continued investment spiraled upwards into the oil sands, the reputation, the public sentiment, and the overall acceptance of the projects declined over and over again over a period of years. Now, what's happening now in the industry? Of course, COVID has displaced a lot of conversation about the environment. There is still much going on, but a lot of it is the attention is being diverted. That attention is going to come back, and that attention is going to come back in a negative way. And it's going to come back in so many levels. We don't even know the impact that it's going to have when all of a sudden all the industries that have been slowly coming back to life, when we see the net result of that. There's already a lot of talk about how the pandemic has been really good for reduction in the carbon footprint and bad for the increase in plastics. But what's going to be the backlash going forward from that? We don't know yet, but I can tell you what's going to happen. Investment in Canada is going to continue to decline. In Alberta is going to continue to decline. We are going to continue to face the kind of criticism and reputational attacks that is unjustified and unwarranted, because we are environmental leaders in this, but we are not leaders in making this visible and public. And that is part of what Aegis and Thermal Trap really focuses on, is making sure that what we do is highly visible. Right now, global leaders are taking action. Companies like BP, Repsol, Total, Shell, as producers, have all made major statements about taking net zero initiatives and bringing them to the forefront. And this is a critical juncture for us in the remediation and the waste management world, because for too long, environmental leadership was coming at the price of profits. Now, that is no longer needing to be the case. Waste management and the waste stream itself does not need to just be a cost center. It can add value. The mission of Aegis and Thermal Trap was to rethink value from the waste stream. And we did that, as Daryl mentioned, by looking at technologies that could turn waste into actual revenue and clean soil. No more dig and dump, no store and ignore. There are so many ways that we can have impact the industry, and all of them have tremendous value. I want to look at some of the, again, from the perspective of business, I want to look at what they're focused on, what the oil industry itself needs to also include in what it's doing. Lower operating costs, more uptime, and faster results. That is and always will be critical to every aspect of any business. And when we compared it to the technologies that were available, rotary kilns, hammer mills, bioremediation, and let's not even talk about dig and dump, we were seeing Aegis producing results consistently, faster, less expensive, and more effective. And in the case of bioremediation, 270 times faster than the average bioremediation project. And that's if the bioremediation project is successful. We know that there's many that aren't. And obviously, everything that we bring to the table and I don't just mean Aegis, but in remediation in general, everything we bring to the table is important. We can't ignore there are places where Aegis is not going to be the perfect solution. However, everywhere that it's a good solution, we want to make sure that our presence can be known. We want to make sure that Alberta's success stories across the entire remediation spectrum can be known. And we can do that in part by being the best performing option in every case. And that was the mission from day one with Aegis and Thermal Trap. When it comes to the actual cost savings that can be expressed in one of the key pieces of it is we're reducing trucked tonnage of materials, 10 to 40%. In some cases, that 10% reduction in truck tonnage doesn't seem like a lot, but when you then shift what's being trucked from class 1 landfills to class 2 landfills, that is a massive impact. With the material that is waste product from Aegis' remediation, 95 to 99% of it is now suitable for Class 2 storage. We're working towards getting agricultural grade storage, but just moving from Class 1 to Class 2 is a massive win. Reduction in tipping fees, again, because we can produce cleaner end product after remediation, reduction in tipping fees have a significant impact on the total cost of this. Recent tests, recent job sites we've run with partners, as Daryl was mentioning at the beginning, we have seen combined savings of 70%. Now, are they always that high? No. Are they going to be that and higher? Yes. That is going to consistently happen. We are looking towards even higher yields of even lower costs to increase the savings. And it all stems from that core mission of Aegis Thermal Trap. Daryl mentioned zero fugitive emissions, 7 to 27% reduction in greenhouse gas across the board. And recovered oil is recovered revenue. And again, this is critical to think about because the industry itself has been plagued by you have to do it because it's the rules, as opposed to now there's more things in it for you. Now, we've always been responsible. We have always been responsible in this industry, in this province, and in this country, exceeding most of the rest of the world's responsibility levels. But we need to take a stand. We need to be in front of that and show our leadership. Whoops, went the wrong way. Where does this work? Works with drill cuttings, invert, SAGD solids, tank bottoms, tailings, cleanouts, and of course, it works with soils, sands, and spills. Now, when we get into this in more depth, we talk about the end-to-end engineering analysis of it. We look at the specifics of it, but this is really focused on producers, remediators, and waste managements and consultants. And we don't go into details on that today because we want to look at it on a job-by-job basis. And as Daryl said, there's a lot more details that we can drill down to on the specifics of how every level of this system functions. And as you saw on this slide, we actually have mapped out the process and we can understand from sample material to understand what the impact is going to be, what kind of reduction is going to be, engaging with our team to produce a complete solution. If you have any questions, we'd love to answer some questions now, or you can reach out and contact us, Aegis directly, Daryl, or myself. Check out our website or give us a shout. If there's any questions, that we'd love to take on some of those. I'm just gonna pop my screen out here and see if there's any questions coming in.
Thanks, Robert.
Okay, thanks much, Robert. Great presentation. At the moment, we don't have any questions posted, and we're just on time to start our next presentation.
Perfect.
And it is my pleasure to introduce Dr. Vicki Friedman, who is the Pacific Northwest National Lab Soil and Groundwater Program Manager and leads the Deep Vado Zone program. She will speak to us about remediation of radioiodine at the Hanford site. Can we please switch presenters?
I think we're in the process of doing that right now. Can you hear me okay?
Yes, thank you, Vicki.
Okay. All right, thanks for that introduction, Parisa. Today, I'm going to be talking about a technology assessment that we did for radioiodine at the Hanford site. Some of the work that we do at Pacific Northwest National Laboratory assists our local DOE office, Department of Energy office, in cleanup of the Hanford site. And so part of what we did was, looking at the Hanford site here, of course, it's located in southeastern Washington state, which is just south of the Canadian border. It's a legacy nuclear waste cleanup site, and there was a feasibility study that was performed in 2012. And the outcome of that feasibility study that was performed in 2012 for this area right here in the red box was that there wasn't anything.
Sorry.
I'm sorry?
Sorry to interrupt, could you please put in presentation mode? The screen is very small to see the map.
Okay. I've had the experience where I'm in presentation mode that it doesn't change slides, so you'll have to let me know if that happens.
Oh, okay, we'll let you know. Thank you.
Okay. So the outcome of that feasibility study was that there wasn't any technology that was currently available to address radioiodine in the groundwater. And so as an interim measure, the hydraulic control system with a pump and treat system that is located in this area was put into place. And then as part of the interim record of decision, there were 3 elements that were identified as needed. One was, was to identify a little bit more information. Little was known about radioiodine and its transport in the subsurface. A second avenue was to look at potential remedies associated with radioiodine cleanup for both in situ and ex situ applications. And then while we were considering those aspects, to also look at whether or not a applicable or relevant appropriate requirements or an ARR technical and practicability waiver was appropriate for this area. So just a little bit, I'll go through a little bit of a description of where the plume is located. You saw that with respect to the Hanford site, it was located sort of in what we call the Central Plateau. Within that center of the site, there's actually an environmental restoration disposal facility, a landfill that is located, and it sits right above the core of that iodine plume. And as you can see in the pictures that are shown here, the expansion of that facility is right along the same path of the plume trajectory. Plume's pretty large. It certainly wasn't the largest plume that you saw on the previous slide, but within that area, it covers 3 kilometers squared. It's 1.2 kilometers wide, and it's fairly thick, so it has a thickness of about 45 meters. And in addition to that, there's also a lot of stable iodine or iodine 127 that is also present in the aquifer, and it's there at much greater concentrations than radioiodine. And that creates problems because, of course, remedies are not really specific for a particular iodine isotope. They don't know to, collect I-129 rather than the I-127. And we performed some recent resin analysis at the pump and treat facility, and one of the resins captured iodide and saw that the ratio of iodine 127 to iodine 129 was at about a 1,000 to 1. So it's not a consistent ratio within the aquifer, but it's still fairly high. And so that is a challenge when it comes to sort of cost-effective treatments at the Hanford site for radioiodine. We don't really know where all the stable iodine came from, but as part of historical operations at Hanford, large volumes of nitric acid were used, and they are known to have a trace constituent of iodine 127. So it's possible that that's the origin of where the iodine 127 came from. So the other thing that we learned when we started looking at the conceptual model for iodine and looking at potential remediation technologies is that iodate is the predominant species in Hanford groundwater, and it was previously thought that the predominant species was iodide. This was actually kind of a good outcome because iodate actually is retarded more in the subsurface. It co-precipitates with calcite and iron oxides, and so it doesn't move as freely in the environment as iodide. And this was also a little bit of a surprise because it was thought that like I said, that iodide would be the predominant species, but we also saw that there was organoiodine that was in fairly significant quantities as well at the site. And whether or not organoiodine was retarded more in the subsurface was really dependent on the particular organic species. And so it wasn't really something we could rely on in terms of natural attenuation. So our approach was, in terms of performing the technology review, was to first look at the literature to identify promising technologies, because as part of the CERCLA process and part of what DOE does is they do a technology pull. They look to see what's out there and see if anything can be adapted for a particular application. After we identified promising technologies, then we moved on to some laboratory scoping tests. And then from the laboratory scoping tests, then there was a down select where we looked at evaluating whether or not treatability testing was needed. And really that was based on our ability to meet the maximum contaminant level of 1 picocurie per liter in groundwater. And that is the lowest drinking water standard for all radionuclides in the Federal Register. So the technologies that we looked at for further screening was really, after that literature review, was organized into 3 separate categories. There was one where we looked at in situ sequestration. We looked at, like I said, we know that iodine or iodate co-precipitates with calcite. There's also potential for apatite absorption and co-precipitation, organic sorption, whether or not chitin, lignin, or humic acid, for example, could be used as an in situ remediation approach and to sequester the iodine in place. And then iron oxide sorption and co-precipitation was also a potential technology that we looked at for in situ sequestration. We also looked at technologies that could enhance pump and treat extraction efficiency, and identified dithionite as one that could potentially be used to release iodine in the subsurface. And then in conjunction with that, if you're going to use something like dithionite to release it, then you also need to use an ex situ extraction within that pump and treat system. And so we looked at different types of materials that could be used. We looked at a ferrihydrate. We've also looked at some bismuth-based materials that could be incorporated into resins. And then we also looked at some commercially available resins as well. We did not look at any microbial-based technologies for this evaluation. And that was because in our process of doing the conceptual model identification and transport, we saw that that they were sort of a second or third order process, and it was not really significant enough. And also the pump and treat system at the Hanford site that's currently operational at the time there was a biological treatment system in place, and there were operational difficulties associated with ex situ treatment. Okay, so we performed laboratory screening of these potential technologies. When we looked at the potential to use calcite as a co-precipitation mechanism, we only saw 70% removal of iodate. And that's the predominant species in the subsurface, but it wasn't efficient enough because of the presence of I-127, and that would not yield concentrations of iodine 129 beneath the drinking water standard. And then we looked at apatite, the use of apatite through sorption and co-precipitation mechanisms, and saw that there was minimal removal, and so that was considered or was removed from the consideration of potential technologies. And then we also looked at this organic sorption. We found that only chitin was effective for iodide, but we didn't see any iodate retention with any of the organics that we used in the laboratory testing. So again, that one was eliminated in our technology screening. And then iron oxide, sorption and co-precipitation was actually fairly successful. We saw that it removed up to 98% of iodate in the subsurface. It also worked for iodide, up to 70%. We saw that iodate sorbed, and both iodate and iodide could be incorporated during ferrihydrate precipitation. And so that one was identified as a possible treatability candidate. When we looked at dithionite, we saw that there was up to four times more iodide that was released, and about 3 times faster leaching of iodine. And so that one was identified as well as a possible treatability candidate. And you can see here over on the right-hand side, it's showing that with dithionite treatment, then you're seeing an additional amount of iodine that is leached from sediments. And then in terms of non-commercial materials, we looked at ferrihydrite, these bismuth-based materials as well. All of them had a high affinity for iodate, and they were effective even in the presence of iodine 127. And so these were also considered possible treatability candidates. And then we also looked at some commercial resins. There was one through, I actually can't remember the company right now, but there was one called CMH20. It was a hybrid type 2, strong base anion resin containing some cerium phases. And then we looked at one called ASM10HP. The company was RemTech. And that was also a strong base anion resin, and it contained kind of a ferrihydrate-like phase. And so those were also considered potential treatability candidates as well. So in this sort of the decision as to whether or not technologies went forward into treatability testing, we looked at the ROD requirements, and the ROD stated that if one or more viable technologies are identified, treatability tests would be conducted for those technologies. And we had considerable discussion around what was considered viable. From certainly, from a researcher's point of view, if it was viable, it meant for me that it showed promise, and that we could, with some time and resource investment, then we could perhaps apply that and mature that technology for application at the Hanford site. But from the contractor point of view, where they needed to go out and actually apply the technology, it was more about, is it ready now for application? And so we kind of performed two different, or had sort of two main considerations in terms of that technology evaluation. We used sort of the standard EIC evaluation based on scale up as we went from batch to column experiments. And we said, well, is it effective? Is it implementable? And what is the cost? Because it needed to be cost effective. But we also looked at this sort of second aspect that's not typically used in these EIC evaluations, and whether or not it was a mature technology, and what's the deployment timeline for FS readiness in terms of the feasibility study. And so so we use this figure that's shown here at right to communicate with the regulator and with the site contractor in terms of just identifying whether or not it was ready for in terms of its evaluation. And so this circle right in here kind of shows if it was red, it's not evaluated as ready. If it's yellow, it's potential, and if it's green, it had a green light to go forward. And down in here, we provided what our assessment was of the technology readiness level. Conceptually, if it was a technology readiness level of 3, technology readiness level between 1 and 3, then it was just sort of conceptual in nature. If we were able to provide a lab proof of concept, it was between 4 and 6. And if we were scaling it up to maturity, it was between 7 and 9. And so I'll walk through now what the outcome of that evaluation was. So for the iron oxide precipitation, what I'm showing here at left is the standard kind of EIC evaluation. And overall, we said in terms of, you know, its effectiveness and its cost, it was probably had a much higher technology readiness level, but in terms of its implementability, it sort of got the red light. And the reason is because the location of the plume, where it's beneath that landfill, the number of wells that would be needed in order to effectively treat this fairly large plume that had a fairly large thickness, that it would be very difficult to implement. And then in terms of the viability of this technology straight off, was that it was just the technology readiness level was too low and that it needed further development. And so it really weren't able to push this one forward into treatability testing. And then in terms of the dithionite, you can see in terms of both the EIC evaluation and the FS viability, even though the technology readiness level was a little bit higher than it was for the ferrihydrate, it still had a lot of deployment uncertainties associated with it. And I think what put sort of a major stop to this technology moving forward were sort of the secondary effects of treatment. So there was already iodide bound to sediments, but as you if you injected dithionite into the sediments, you could get some following with release of you know, sulfate and other anions that could kind of muck up the resins in the pump and treats facility. And so from an implementability standpoint, it was considered not ready for treatability testing. And then we took a look at some of the non-commercial resins, and these were really some of the most promising ones. In terms of potential viability, there was some good material performance that we saw on some of these, so especially the bismuth-based materials. But in terms of the viability from sort of a feasibility study standpoint, they weren't ready for deployment. And so because of those significant uncertainties associated with the technology development, we ended up having some poor column performance when we integrated these materials with pan beads. Those, again, were rejected as potential treatability testing candidates. And so when we looked at the commercial resins from RemTech, we did some column testing scale up. The area that I'm talking about in terms of where the iodine 129 plume is located is located in an area called 200 West. And so there was some 200 West groundwater that was supplemented with iodate and to meet the same concentrations of stable iodine. And then we did a comparable flow rate in those column tests relative to the pump and treat system. And we were able to determine that in order for it to be effective, it would have to be effective at like a 3% breakthrough. And that would be based on just reaching this very low drinking water standard of 1 picocurie per liter. And so what we found was that there was a 3% breakthrough occurred after 125 pore volumes for both of these resins. And so you can see here in this breakthrough curve that there was a pulse of iodate that was greater than 1, which likely shows some interaction of the groundwater constituents as well. And so what we saw there was pretty marginal performance. And when we compared it to that performance to the other resins within the pump and treat facility, so we use a Dow-X resin for uranium treatment, and that treatment was at 100. Treatment capacity was 100 liters per gram of resin. The Tech 99 using a Purolite resin, 10,000 liters were treated per gram of resin, but the iodine was only 1 liter. And so it really was not a cost-effective option. And there was still this additional issue of groundwater constituent interactions that would need to be addressed. And so again, this one was associated with sort of kind of a low sort of technology readiness level because more money needed to be invested in order to bring this technology to maturity so that it can be implemented at the Hanford site and treat radioiodine. And so again, you know, it's not only that the resin performed well. It'd be quite expensive to trade out the resins as frequently as required. And then again, you have that plume core that's right beneath that landfill, that ERDA facility. And so drilling wells would be very tricky in terms of being able to extract water, probably from a down gradient from where the down gradient from the ERDA facility itself. And so the practicability of all those candidate technologies was pretty low, and it was largely driven by both the site contaminant properties that hindered effectiveness and also the implementability, and just in terms of having this sort of large dilute iodine plume that is located right beneath this landfill. And so it creates a lot of challenges in terms of treatment at Hanford. And so in terms of the effectiveness, implementability, and cost evaluation, that CERCLA process is there in place to require treatability testing as for existing technologies, and it is not really there for making investments and maturing technologies. And so for that reason, a lot of what was done in terms of this technology evaluation that we did for the Hanford site is being currently used to support a consideration of a technical and practicability waiver. And that is a kind of a first of a kind waiver that's being sought for the Department of Energy. There have never been granted, there hasn't been granted a technology and practicability waiver for any sites with the Department of Energy complex, and there haven't been any that have been granted either for radionuclides. And so it's a process that we're involved in currently there's a lot of questions, I guess, that will need to be addressed in the future. And so that's what we've been looking at to support work at the Hanford site. And so with that, I can answer any questions you might have.
Thank you very much, Vicki. That was an excellent presentation. While we wait for some questions to come through, I have a question to ask you. You mentioned the decision framework that went into some of the consideration for the different technologies. Were there other, in terms of effectiveness and cost, and were there other sustainability metrics that went into the consideration as well?
I don't think we got that far in terms of sustainability, because there was just, it really came down to, we've got this really large plume. We can't drill wells into the core of the plume. And so it was really, we sort of categorized what we thought we could do. And when they weren't really effective enough, sustainability wasn't an issue because the technologies themselves just weren't effective enough.
Yes, thank you. I suppose those are also cost and effectiveness also come into play as some of the pillars of sustainability. So those were in a way considered, but I guess not everything, because as you said, it didn't go that far into the.
Yeah, they're sort of indirect considerations, right? Because you're kind of considering sustainability along the way.
Yes.
Yeah. So agreed.
Okay. Yes, thank you. So we have, just looking at the questions online, we have some questions for the previous talks that we did not get to, and we have a few minutes before we move on to the next presentation. And some of those are for the phytotechnologies. And one is that how effective is this in an arid region in southern Alberta? And this is a question by Karen de Raldis. If Elizabeth, if you're online. Just give a few minutes for Elizabeth to unmute. Okay, so maybe we can park those questions for later on, or you can reach out directly to Elizabeth Marie for phytotechnology related questions. And we have other questions for Kevin at Vertex. If you're online, Cole Kaiser was asking for in situ injection, what pressures were observed? Okay, it may be that we don't have all of the previous speakers available or unmuted and able to speak. So thank you again for the great questions. There were quite a few of them. I have wrote some of them down or recorded them, but if you can reach out directly to the presenters at the end, that would be great. So moving on to our next presentation by Brandon Smith and Khalid Lamouji, who are the co-founders of Analytium Solutions, who will be speaking to us about integration of automation and machine learning in environmental assessment.
Hi, can you hear me?
Now we can hear you, Brandon, yes.
I'm just wondering which slide you're viewing. Are you viewing the presenter's view or the actual presentation?
It is the actual presentation. So if you could change the display settings.
How about now?
Excellent, good.
Okay, great. So today we're going to talk about practical solutions to liability management through integration of data automation and machine learning. So over the past few years, we've shifted our expectations of data. Most people didn't notice it because it integrated pretty seamlessly. We had algorithms running behind the scenes, selecting what you see on your phone or how you interact with your smart home, and they were constantly collecting data. They were curating and cleaning that information such that your interaction with your data actually felt natural. Why then is data-driven decision-making so elusive in environmental assessment? Well, we're going to start by untangling that and looking at where opportunities exist for us to simplify these processes and really cut the noise. And best of all, we're going to provide actually a real-world example of how we applied automation and machine learning into that environmental assessment. So what do we all have? Well, we all have ingredients. We all have the data to make decisions. What do we all want? Well, we want pizza. We want to assess and analyze our data in meaningful ways. But how are you going to assess that data? There's no lack of tools out there available to us. There's ArcGIS Online, Azure, cloud-based systems. There's Power BI and Tableau, Equus for data, SQL, Oracle. If you're into modeling, there's ModFlow, Surfer, Hydras, vFlow. Ultimately, we're becoming inundated with the number of tools we have at our disposal. But what are we doing with all these tools? There's no lack of marketing out there that tells you you need them in your kitchen. But just arming yourself with a pantry of ingredients won't suddenly revolutionize how you're doing assessment or how you're cooking your data. To find that solution, you need a chef who knows the recipe of what you're trying to make. So what does that really look like? Well, for us, it's the connection between a customer, the ingredients or tools, and the chef. And the chef is a data scientist. It's a statistician or a programmer. The tools you need are fit for purpose data analytics. And the customer is actually a subject matter expert. Now, this is the part we've been missing historically. And it's the reason we really need to consider the connection between data scientists, fit for purpose tools, and subject matter experts. And it all really boils down to time, cost, and quality. Now, traditionally, you can really only choose two and the third's going to suffer. So you can have a high quality product and you can turn it around on a short time frame, but it's going to be really expensive to do that. What we're hoping to showcase today is that with data-driven analytics, you can achieve higher quality results in less time for lower cost than previously possible. And further, you can do it with the same ingredients you already have. So what does that look like? So Lithium was actually really fortunate in that we were able to team with 360 Energy Liability Management and ClearSight Solutions on a series of projects that exemplify this approach. To steal 360's own words, the goal was make closure simple. ClearSight provided risk analysis and Lithium supported with data analytics throughout the entire process. So what were the project highlights? The program was 16 site-specific risk assessments and risk file reviews. These sites had long histories of reporting. Various consultants had worked on them. There was numerous handovers, lots of ingredients to work with. Deep impacts, various parameters of concern. It's primarily salts, but there were also hydrocarbons, glycols, methanol, presence or potential presence of historical transformers, so PCBs. There's active monitoring and assessment programs and plans for in situ remediation systems. So we've got this mixed bag of solutions being presented and an ever-changing foundation of data. And there was complex lithology. Some of the sites had coal seams or coarse gravel units, high natural salinity that complicated the picture. So the first goal in all of it was really focus on the original question. How do we progress a site to closure and make that process simple? How do you pick the ingredients for your kitchen and find the recipe that's going to make the pizza, right? So, like I said, we all work from the same ingredients, but there's really only one recipe that will result in a cost-effective liability management system. So with that introduction, I'd like to hand it over to Lithium's principal data scientist, Khalid, and he'll walk you through sort of the process of how the case study came together. Khalid, you may still be on mute.
Can the organizer please make sure that Khalid is unmuted or allowed to unmute, please?
Hello? Hello?
Hey, you're good now, Khalid.
Oh, great.
Okay.
Great, thank you. So thank you guys for inviting us. So let us do some cooking here. Brandon, can you move to next? Thank you. So basically, there is one process. One sec here. Yeah, and the process. So basically, there is one process. Well, there is multiple process, but there is always one that's optimized. That you want to optimize. You want to be easier, faster, and straight to the point. And that process, generally in data science and machine learning, has 4 or 5 steps. The first step, or the most important step, is defining the objective. the questions, the business question that you want to answer. And it has to be very specific, that you sit basically, so the Brandon 360, what do you want to have? Then as soon as they, okay, well, that's what you want to get, then what is the ingredient? What kind of data I need? Do I have it? Maybe I don't have it and I cannot get what they want. Maybe I have it, but it's in different places, some in PDF, some in SQL, some in Excel, and so on. So how can actually I access it and I bring it very smoothly? Now I have it in hand. The next step, how can I clean it? Which is basically I want to match the soil data with the groundwater, the chemicals with the locations. If there is any missing value, how to deal with it. There is no the text, also how to deal with it. And now I have them clean and nice in one place as a file, which is basically ready to be consumed by the model, which is the next step. So the model basically is the connection between the data, which is numbers, and the answer and the information. What the model does basically, it just put the picture to you. It said, okay, well, here is the trend. And for the model, actually, there is two steps. The first one is data visualization. Humans are very visual. You put data out there, you want to slice it, dice it, see a play, such as your brain is putting the connection. And that says, okay, well, I see that the trend is going up. It's not linear, and probably I need, this model, this mathematical model, or statistical model, or machine learning. So this is basically the first step. There is one last step, it's important, which is basically when you have the model, how to communicate it. Most people don't like statistics. They find it like hard or black box and so on. So if I go to my boss, is not statistician or data scientist, how to communicate very easy for him. So it's actually just by clicking, he can run the model, or by clicking, he can get the results. Still intuitive for him, he understands it, but it's easy to run. So let us apply those 4 or 5 steps. Then there's one another steps. When you get all of this, how you actually can automate this system. The data is coming, it's crunching, it's visualizations. I'm giving to my boss. Now he can, if he ran any other data, any other site, or 100 or 1,000 sites, he will get the same result. So basically, I'm removing the repetitive task or the noise, which is the human, so such I can make it very smooth for him or them or so on. So let us apply actually the example, clear site example. So the example, and we're following this step. So the first step was defining the question. And the question here, again, as I said, the most important step is defining the question. And this one generally take a lot of talk. It's like, what do you want? Sometimes they say, the client says something, but that's not what it means. So like, what do you want exactly? I want tool. In this case, we define the objective as being a tool which is simple, interactive, which is data-driven and defensible, which means basically the model that we are running is open source. It's open. People can see what it does. Such as if they go to the government and said, well, we believe, that the contamination is going down here, they have to prove it. They say, yeah, look, it's significant with 95% confidence and so on. And you can see the line, no black box in this case. So this is the definition about the tool. Then the tool, we wanted to answer 3 questions. 1, the volume of contaminations. 2, the concentration of chloride over time at the receptor. And 3, the number of redundant groundwater wells. Hopefully we can reduce the groundwater network monitoring. So the tool has certain specificities, characteristic to do 3 main things. So now we are in the tool. So you remember the first step was like defining the objective, how the tool, what you wanted to do. The second, I need the data. So we're gonna go get the data. Here in our example is from Excel. I think there was also some PDF, we extract it. Then we want to put it somewhere which is accessible. Most of data that we have is not accessible. It's hard for statistical software or machine learning to access to. And this is actually take a lot of time to clean. But soon you want it somewhere which is clean and digestible, but by the model. And in this case, generally, like tables, what you called tables or metrics are good for that. And so we got the data, we clean it, we match it, then we put it in table, in a file, it's saved. Then we made the table filterable. So basically you can choose which data set you want to see. If you have 100 let's say sample, you can choose the first 5 or 1 and 6 and 20, or only the background, or only samples with chloride above certain. So we want to give the client this ability to slice and dice and play forward, backward with the data, not only one way. Here is data, here is the plot. The next step, you remember, is the modeling data visualizations. For spatial data, in this case, you need visualization over space. So basically you want to know where it's located, right? And if you want only sample 1 and 2 and 3, you click on them, it will highlight for you. If you want anything below certain, it will highlight for you. Now, but you have only the points. What people want, or the brain understand, is not the points, is the heat map. So you kind of interpolate it. So you click actually in the tool, and automated is interpolate for you to give you an idea about the contamination on the surface. So now I know it is my contamination, but also it gives me the volume, the surface. Kind of like, this is the surface. Remember the question was, I want the volume. So cool, this is my surface, but I want also the depth. Therefore, we added another tool, which is 3D. This is all interactive, by the way. So you can zoom in, zoom out, play with it, and so on. So almost full integration between all the components. So you say, okay, I want to see what is the contamination on the right-hand side. Which depth? You go all the depth to see, yeah, it's point this and this, and in between, it's say 5 and 7 meters. So I know the depth now, and I know the surface, the depth on the right-hand side, the surface, multiply them automatically, actually, and it gives you the volume, say 500 meters cube. Cool. So the first question we answered so far. We go to the second question. So the second question was, is there any change or how concentration of certain chemical? Here is chloride changing over time. So the same again, step 1, we define the question. 2, we get the data. We have data over time. We put it on filter on the table on the right-hand side. On the left-hand side, the right-hand side is a map which is interacting with the table. So we slice the table. It changed the data. Then we added the other component, the second component, to the heat map. Same, it tells me where the groundwater is, basically has high value of the chloride. Then we add another component. We added the trend over time. You remember for the soil, we did not have the time, therefore we cannot have the trend. So we did not have the ingredient for time. But this one we have spatial and time. So automatically what it's telling you, you can have information in space, but you can have also information about time. And this is basically bringing us the idea that the data basically tell you what you can do, or what you can do tell you which data you want, but also the data tell you what you can do or what you can do. So we add that component is interactive, and it's basically here, you can see interactive, you can click on any, or you just leave all the 20 or 30 walls and you see all the trends. And if you choose EC, it'll give you ECs automatic, a drop down, and you choose, and it gives you the trend. Then of course we want to estimate the trend. There is another button, you click on it and it can, okay, here is Mancondle, here is the slope. So actually it has all the components, such as you plot it, you see the heat map, where is it, but you see also where the chemicals are changing and where are not changing. Basically, if it's not, you know that your plume is stable at certain places and not stable in other places. And since if it's not, let's say, stable in other places, you know how much change, is it fast, slow, and so on. So you can actually add more component if you want, based on what the client wants. And this information now give us or allowed us to build statistical multivariate statistical tool that actually can forecast any concentration of chloride here over time. So because you remember, we have the location and time. If we gather this information, it will allow us to build systems that, okay, well, here is my concentration, here is how it's changing over time. So that was second question, how my concentration of certain chemicals is changing over time. Then we go to the last question, which is, okay, well, cool, I have all this information. Can I use it actually to cluster the wells based on similarity? So basically breaking the wells such families who have certain behavior. In our case here, we can break it on chloride behavior over time. You know, that means correlation between well 1 and well 2, there is higher correlated, that means almost the same trend. That means basically they're telling me the same information. I'm getting more data, but not a lot of information. So I'm just wasting basically my resources to gather data that I don't really, it's not I don't need, but does not have much value. So here, for example, it gives us 2 groups and one group has 4, you know, the red are the 4 wells, and it said they almost have the same behavior. Probably you guys can reduce this only 1 well, and the same for the second group. And therefore, at least we can probably reduce 3, 4, or 5 wells. Of course, you know, you have to sit with, this is just the tool, but you have to sit and say, yeah, okay, they are almost same information, same variation, it's to replicate, and so on. Probably we should reduce this well. So in summary, I'll summarize what we have done so far. So what we want, we want tool which is simple, interactive, and use data and defensible, which means basically a white box. And we want this tool to estimate, to answer 3 questions. And also we want it to be fast. That means it can be automatable, and that means we can automate it. Then we want it like all repetitive tasks can be repeatable. So I repeat again. So we want visual tool, which is visual interactive, high quality. That means the math and stats in it can be defensible in front of a regulator or the client or anybody else. Fast. That means repetitive tasks can be automated to reduce time and human error. Things that are repeatable, we don't read to do it again. And low cost, which means basically I need JS and the statistic and the trending and the visualization in one place. And by the end, there's one characteristic is like, can we integrate it? Can this tool be integrated in our system, such as ClearSight can just access it from there. You put it in this system. You don't have to pay, which is we add this component. So thank you, and I let Brandon finish.
Yeah, thanks, Khalid. So with that, you know, there's almost 2 deliverables. There's the case study of Analytium in providing detailed analytics that allowed the people who worked on the project to focus on what mattered, reduced the noise to just the few ingredients or the few data inputs of importance. They also provided the data analytics on a single platform. So that single platform allowed communications with project managers that were in charge of the program, so 360s, project manager team, but also different people have different views of what data is important to them. You know, if you're the reclamation person looking to see the direction to site closure, it may be surface data that you find of most importance, right? It's that routing zone, versus if you're the hydrogeologist on the team looking to understand what the impact is to groundwater, the focus of your data may be slightly different. So having that all on a single simple platform really facilitated that communication. As Khalid mentioned, volume estimates. You know, those are important in liability analysis because oftentimes we go down these paths of finding overly complex solutions to simple matters. You know, if the remediation going down the path of detailed risk analysis only reduces the volume estimate very small, a limited reduction, maybe there's not a purpose to go all the way down that path because at the end the cost would be the same. So a couple other things that came out of this project was monitoring network optimization, reducing the number of wells that required future sampling, the contaminant modeling aspect, so really having a clear understanding of what the potential risk to the receptor was now and in the future. Visual data communication, it's much easier to communicate when you have interactivity with visual data. It's relatively hard to walk somebody through, a 20-page table and try to point out what matters. And then, as Khalid mentioned, automating that process. So when you made slight changes, we didn't have to go all the way back to the start and restart this process through. It was automated and you could see it in real time. So of course, those were the case study results and how Analythium supported the team. But the real question today is, how do we generate cost-effective liability management with that? So, a detailed look at the data you already have available without that endless cycle of having to go and collect more data. We were actually able as a team to complete all 16 risk-based reviews without collecting anything additional from the site. Same data, but very different outcomes. We eliminated COPCs, which weren't a potential for risk. And in one instance, we actually changed the projection of a site from what was going to be the potential of a relatively expensive in situ remediation system to simply a source zone remediation and an acknowledgement that there actually is no potential for risk because the models that were run indicated that contaminant migration would never occur to the level where it would reach a receptor above the guideline. Clearly defined path to closure. So substantive reductions in overall liability are important, but so too is understanding what the prospect of the site looks like in the next 1 to 2 years. And the reason that's important is for site managers that have large portfolios and they're trying to do cost forecasting, that understanding of what the site's going to look like, next year and the year after, and not just giving them the idea that we're going to collect more data next year, but really giving that simple, what's the path to closure answer is worth its weight in gold. Statistically validated risk ranking. So what I mean there is sites that have potential to cause adverse effect. What's the time frame between now and when that event might occur? And how valid is the model that we're using to make that prediction? The reason that's important is it allows your clients to actually risk rank what sites are priority. Our clients are budget conscious in today's economy. So they have limited resources, and giving them the availability to look at data and understand where those resources are best spent in terms of risk ranking or de-risking their sites is an important characteristic in this. The process also allowed, as we mentioned multiple times, clear communication between the project team. But that visualization is also really important to communicate with the client and ultimately communicate to the client what needs to be done in a way that they can then take that and have their own conversation with regulators or their own consultation with relevant stakeholders, which may be landowners. And ultimately, at the end of it, it was completed at a lower cost and faster with higher quality than previously possible. The turnaround on these 16 sites was about 8 weeks, which is a pretty great turnaround given the length of time that these sites had been sitting in that system of continual assessment and reassessment. So with that, the future of work and the idea of this simple and clear path to closure is really automated data analytics. It's that delivery of the best possible format that conveys the information in the clearest way possible. So with that, I'd like to open it up, I guess, to questions from the audience. And we've just left this slide here. So if you do have questions that follow or that you think of later, you can always reach out to either Khalid or myself anytime.
Thank you, Brandon. Thank you, Khalid. Great presentation. Very interesting applications of data analytics. I don't believe we have any questions online at the moment. I'm monitoring those and I don't see any at the moment. When you have a single client or a single source of data, I can see how you can put it all together, but if it's coming from different parties or different sources, are there any issues with privacy or confidentiality in gathering the data that you need?
So I guess one of the things is there's two forms of the data. There's data that we receive from open source. So those are things like weather pattern data or precipitation information, soil studies, that sort. And then there's the data that we're provided from the client. Data provision from the client, if I'm understanding your question correctly, would be the information that they have. So they have the property, they're the owners of that information. So we work with the client to basically unravel the site history of data that they're in possession of. But sometimes on legacy sites like this, some of that data is old print text style. Go to the cold mountain storage and pull out the box and scan it. But I would say no, there's never really the issue of liability on information storage or use because it's our client's own property. Does that sort of answer where your question would stem from?
Yes, that's right. I thought in some cases there might be multiple parties involved and multiple consultants, and so there might be some issues. I can see there's been a lot of great use of data made when there are public databases available, for example, the California GeoTracker. But this is more on I understand, on an individual site or sites or client-specific data analysis.
Yes, it's site by site, but even some of the clients ask about privacy of the data. That means if we have that software, the software by the end is on the cloud, actually is running on Amazon cloud. But some of the clients will ask and said, look, I don't want my data to be on the cloud. Can you put it on my system? Yeah, in this case, actually, you can do it. You just take basically the tool and put it in the system on premises inside, and that's it. So it's very flexible system that can basically do almost anything the client wants. Why? Just because we're using open source. You know, all the components are there. We're just basically leveraging this component that exists everywhere and creates basically the piece that the client wants and how you want to see it and where you want to put it on whatever he wants or she wants.
Okay, thank you. I understand now. So thank you to the presenters and the attendees for your participation in this session. Great questions and good to see the promising advances in the application of technologies for sustainable remediation. The questions and the answers both highlight challenges and opportunities for more sustainable options to remediation. Thank you, everyone. Enjoy the rest of the conference.